Hello and welcome to Machine Learning with Python 02 GBMs. This is an online, beginner-friendly and practical certification course offered by Jovian. Today we're on Lesson 2, Logistic Regression for Classification. My name is Akash. I'm the founder and CEO of Jovian, and you can find me on Twitter on @AkashNS. So let's get started. The first thing we'll do is go to the course page 02gbms.com. If you haven't enrolled in the course already, just click the enroll button and you will be able to participate in the course. Now we're currently doing a live run of this course which started on the 19th of June and will run over 6 weeks. But in case you're not able to join us during the live run and you're watching a recording, that's perfectly fine too. You can still complete all the assignments and build a project and earn a verified certificate of accomplishment. During this course, you will watch a hands-on coding focused video tutorial every week. Then you will practice coding online with cloud-based Jupyter notebooks and solve 3 coding assignments and build a real-world course project where you'll train ML models using a large real-world dataset. Now there is a prerequisite for this course, which is the Data Analysis with Python 02 Pandas course. If you haven't taken this course already, then you can take this course alongside the machine learning course. This is an easy course to follow and you can watch lectures, complete assignments and build a project for this course too. Now on the course page, you will be able to find all the lessons and assignments. Last week, we looked at lesson 1, linear regression with scikit-learn. This week, we're looking at lesson 2, logistic regression for classification, and assignment 1, train your first machine learning model. So let's open up lesson 2, logistic regression for classification. On this page, you will be able to find a recording of the lesson and some information about the topics we are covering. Below, you will find a lesson notebooks tab, and here is the code that we will look at today. So this is a Jupyter notebook and you can read the explanations in the Jupyter notebook and you can scroll down and you can see the code as well. If you want to run the code, just scroll back up to the lesson notebooks tab, click the run button and select run on Colab. When you select Run on Colab, you will be asked to connect your Google Drive account with Jovian so that we can take this Jupyter notebook and place it within your Google Drive, and that notebook can then be executed using Google Colab, which is an online Jupyter notebook execution platform offered by Google. If you have any questions at any point while watching this lesson or while working through the notebook, please feel free to ask them on the discussion forum. So just open up the discussion forum link here. This will bring you to the forum category for this lesson and click new topic, type your question and post it, and you will receive an answer in just a few hours. So quick recap, go to 02gbms.com, enroll if you haven't enrolled already, open up lesson 2, scroll down to lesson notebooks, click the run button and select run on Colab to run the notebook. And that brings us here to Google Colab. So the topic for today is logistic regression with scikit-learn. And here is a quick overview of the topics that we're covering. This image will give you a hint of the problem statement that we're looking at today. So we'll start by downloading a real-world dataset from Kaggle. We will explore the dataset. We'll perform some exploratory data analysis and visualization. Very little. We will then split the dataset into a training, validation and test set. So we'll talk about why these are important. We will talk about filling and imputing missing values in numeric columns. We will also look at how we can scale numeric features to a 0 to 1 range. We will also look at encoding categorical columns as one-hot vectors. Then we will train a logistic regression model using the scikit-learn library. Then we will evaluate the model using the validation set and the test set that we had created. And then we'll save the model to disk and load it back. So you'll see quite a bit of overlap between what we are doing today and what we did last week. And that is intentional. The idea here is that the machine learning workflow is something that you will apply to pretty much every machine learning problem you solve. So by looking at it multiple times with multiple data set in the context of different machine learning algorithms, you will start to get used to it. And by the end of this course, this should become second nature to you. And you can see instructions on how to run the code. We are currently running it on Google Colab using the run on Colab option, but you can also run it on Binder. It will be a little slower or you can run it on your computer locally. Just use the run locally option by clicking the run button. So here's the problem statement that we're looking at today. Since we want to take a practical and coding focused approach, we will learn how to apply logistic regression to a real world dataset from Kaggle. So here's the dataset. The rain in Australia dataset contains about 10 years of daily weather observations from numerous Australian weather stations. And this dataset is taken from Kaggle. If you open this link, you will see here the page where this dataset is taken from. So Kaggle is a platform where you can participate in data science competitions, and Kaggle is also a community where people share datasets and data science projects. Now, on this dataset page, you will be able to browse the dataset. You can see some information about the dataset. As it says, this dataset contains 10 years of daily weather observations from many locations across Australia. And the objective of this dataset, or why it was created, was to predict next day rain. So we'll talk about what that is. You can also see the columns in this dataset. So it seems like there are about 23 columns in the dataset. And you can see that these are the first few columns. The date of the observation starts around 2008, goes on, or 2007 in fact, and goes on till 2017. It contains information like location, for example, Albury, Canberra, Sydney. It contains a minimum temperature for the day at that location, the maximum temperature, rainfall, evaporation, sunshine, etc. So a bunch of different measurements of weather at several locations day by day for almost 10 years. That's the dataset that we are working with. And here's a sample from the dataset, just to give you a context of what it looks like. Now, as a data scientist at the Bureau of Meteorology, you are tasked with creating a fully automated system that can use today's weather data for a given location to predict whether it will rain at a location tomorrow. Okay. So if you look at this dataset, you have all these columns of data: location, min temp, max temp, etc. A total of 23 columns. Not all of them are shown here. And then there are a couple of columns at the end. One says rain today, which indicates whether it rained on this particular day. And the next is rain tomorrow, which simply indicates on whether rainfall was recorded the next day. So for 10 years of data, we have all these weather measurements. And then for each day, we have also listed whether it has rained on that location on the next day or not. Now, this is very useful because now we can use this 10 years of historical data and create some kind of a system which can take the data for today and use that to predict whether it will rain tomorrow. So it's a weather prediction system that can potentially replace a meteorologist. So that's what we're trying to create. We want to create this forecast. Specifically, we want to create this rain forecast, whether it's going to rain or not in a particular location, given its weather information for today. And here is some of the information you have. So before you proceed further, just take a moment to think about how you can approach this problem. Maybe try listing 5 or more ideas that come to your mind when you are executing this notebook. It's important to think about this because machine learning requires a change in mindset, and you can see how your original mindset is as you list out some of these ideas. And once we work through the machine learning approach, you can try and see if you need to change your mindset a little bit so that the next time you come across a problem, you can think of it in terms of a machine learning algorithm or not. Okay. So in the previous tutorial, we attempted to predict a person's annual medical charges by looking at information like their age, their sex, their number of children, whether they're a smoker or not. And there we use linear regression. In this tutorial, we are going to use logistic regression, which is better suited for classification problems, like predicting whether it will rain tomorrow. And identifying whether a given problem is a classification problem or a regression problem is a very important first step in machine learning. So let's define these terms, classification and regression problems. Problems where each input must be assigned a discrete category, and sometimes these are called labels or classes, are known as classification problems. And here's what I mean by that, with some concrete examples. Rainfall prediction, predicting whether it will rain tomorrow using today's weather data. So what we want to do is take all the information for today, all the measurements for today, and then using that, either say that it will rain or say that it will not rain. Okay, so there are two categories or two classes which we want to classify these measurements into. Whether these suggest that it will rain tomorrow, whether these suggest that it won't. Here's another one, breast cancer detection. This is actually something that is used in the real world, predicting whether a tumor is benign, which is non-cancerous, or malignant. So if a tumor is detected in your body, can we predict whether it's cancerous or non-cancerous using information like its radius, texture, etc. So once again, we are classifying tumors into cancerous or non-cancerous. Here's one more, and there's a data set that you can click through and find to do exactly this. Here's one more. Loan repayment prediction, predicting whether an applicant will be able to repay a home loan based on factors like age, income, loan amount, number of children, etc. So here we are not predicting medical charges, which is like a continuous dollar number, but rather we are predicting whether they will be able to repay a loan or not. So yes or no. Again, a classification problem. And then there's one more, handwritten digit recognition. So here you are given pictures of handwritten digits. Here you're given pictures of handwritten digits, and your job is to identify which digit a picture represents. So you can click through and you can discover this data set as well. In this case, there are 9 classes. You have to classify whether the digit is a 0 or a 1 or a 2, 3, 4, 5, 6, 7, 8, 9. So actually there are 10 classes. So classification problems can be binary, which is yes, no, will rain, will not rain, benign, malignant, will repay the loan, will not repay the loan, or they can be multi-class where you have to assign each input into one of many classes like handwritten digit recognition. Try and think of some more examples of classification problems. And once you're done with this notebook, once you work through this notebook, try and replicate the steps we followed in this notebook with each of these data sets, just to get a better sense of how classification problems work. So those are the kind of problems that we're looking at today, but the kind of problems that we looked at the last time, which is problems where a continuous numeric value must be predicted for each input, are known as regression problems. And here are some examples of regression problems. Medical charges prediction. So we are using inputs like age, number of children, whether the person smokes, etc., to predict exact number, which is the amount of money they will spend on medical expenses. Similarly, house price prediction, given information like the location of a house, the number of bedrooms, the square foot area, how many bathrooms it has, etc., whether it has a lawn, can you predict the price of the house? So again, it's an exact number. It's not a yes, no, or a category. Similarly, there's another data set here of ocean temperature prediction, given information about several measurements taken from the ocean floor. Can you predict the temperature of the ocean floor? And you can check out this data set for that. And then in weather itself, if you think about temperature, if we want to predict the temperature for tomorrow, rather than whether it will rain or not, the temperature is again a continuous number. So once again, this is called a regression problem, not a classification problem, because we're trying to predict a continuous quantity. So try and think of some more regression problems that you may come across or you may want to solve. And you can try and replicate the steps we followed in the previous tutorial with each of these data sets. Okay, so that's classification and regression. Classification is just classifying data into certain classes. Regression technically or literally means fitting data. So trying to create a model which can fit exactly to the numeric value that you want to predict, right? So whenever you see regression, think continuous values. Whenever you think classification, think discrete classes. And we saw that linear regression is a commonly used technique for solving regression problems. hence the name linear regression. And in a linear regression model, the target is modeled as a linear combination or a weighted sum of input features. For example, we said that trying to predict the medical charges can be done by taking a linear combination of some input features. So let's say we are looking at the input features age and whether the person is a smoker, so 0 or 1. So the model that we created the last time assumed that age has a certain weight, W1, and smoker 0 or 1 has a certain weight, W2, and then there is a certain number B. So you have W1, W2, and B. If you can figure out good values for W1, W2, and B, then you can take any value of age and any information about whether the person is a smoker or not, and get a good estimate of their medical charges. So that was the model that we had created the last time. And what we did was we took that model, and using that model, and we took random values of W1, W2, and B to get started. We took that model, and using that model, we generated predictions for all the inputs that we had. And we compared the predictions of our model, our randomly initialized model, assuming a linear relationship, we compared its predictions with the actual targets or with the actual medical charges of those people using a loss function, so called the root mean squared error, right? So we compared it using a loss function, and then we trained a machine learning model to reduce the loss function by adjusting the weights W1, W2, and B. Okay, that is what a machine learning training process looks like. So here's what that looks like. We take some input data, training data. So this would contain information like age, whether the person is a smoker, number of children, etc. And it would also have some outputs. So we would put the input data into the model and we would get some predictions from the model. So we would take the predicted output from the model and we would also take the actual output or the real data from the training set, put them both into a loss function, which was the root mean squared error in case of linear regression, and then run an optimization method to reduce the loss by changing the weights within the model. So that will then improve the model over time. And as we do this over and over repeatedly for long enough, the weights get pretty good, and then we can use the model to make predictions on new data, right? That's the machine learning process that we followed for linear regression, okay? And if you want to see a more mathematical discussion of linear regression, you should check out this YouTube playlist that I've linked to here. And that will then go through in more detail how each component fits in and how the optimization works. So for classification problems, similarly, the technique that is often used is called logistic regression. And specifically for binary classification problems, which is the kind of classification problem we're looking at today, just a yes-no classification. So in a logistic regression model, we start out the same way. We take a linear combination or a weighted sum of the input features. So let's say if we just look at today's temperature and today's rainfall, and we want to use those to predict whether it will rain tomorrow or not. So we start out by taking a linear combination. We say we pick a weight W1, a random weight W1, we pick a random weight W2 and a random weight B, and we fix them. So W1, W2, B, we fix them. Then we calculate this quantity for a given input. Let's say we have some information about the city Melbourne. We take the temperature at Melbourne, we take the rainfall at Melbourne, we multiply them with W1 and W2, and we add B. Okay, and we get this quantity X1 W1 plus X2 W2 plus B. Then we have an additional step here. So in linear regression, we were done at this point, but in logistic regression, we have an additional step. We take this quantity and then we put it through this activation function called sigma, called sigmoid. It's represented by this character sigma, but it stands for sigmoid. And what the sigmoid function does is it takes this output of this linear combination and it squishes it between the range 0 to 1. Okay, so the exact details are not very important about how this function does so, but what it does is it takes this linear combination or this quantity that we get, X1 W1 plus X2 W2 plus B, and it squishes it into the range 0 to 1. And then that value which we get out of the sigma function is inferred as the probability of the class that we're trying to predict. So since we're trying to do a yes no prediction, which is it will rain tomorrow or it will not rain tomorrow. So the output of sigma will be a number between 0 and 1, and that number will indicate what our model thinks is the probability that it will rain tomorrow. Okay. And then we compare those probabilities with the actual values. Because we have historical data, we can see whether our model is predicting the right probabilities or not. If it is not predicting the right probabilities, then we penalize it by giving it a high loss. If it is predicting the right probabilities, then we penalize it less by giving it a low loss. But overall, we come up with a loss for the model. And for logistic regression, the loss is called the cross entropy loss. It has a formula like this. Again, the details are not that important. The important thing is that there is a small change in the structure of the model, which is this function sigma. And then this loss is a value which is high if the model predicts bad probabilities, and the loss is low if the model predicts good probabilities. Okay. And then once again, we train the model in the exact same way. So we take the data that we have. So we take the weather data for today, put it through the model, and then we get a prediction from the model. We take the prediction of the model and we compare it with the actual data that we have, because this is historical data of whether it will rain tomorrow. So we have the actual yes, no answers of whether it will rain tomorrow. And we take the predictions, which are probabilities, and we put them into this loss function called cross entropy. We run that through the optimization algorithm. Once again, the optimization algorithms like gradient descent, least squares, there are many optimization algorithms. And that is able to then change the parameters or change the weights and biases of the model, the W1, W2, etc. So that the model now makes better predictions and gets a lower loss, right? So this is the same machine learning workflow that is applied, except that the details are changed. The model now, instead of being just a linear combination, also applies a sigmoid function. So it outputs numbers between 0 and 1. And then the error, instead of being a root mean squared error, is a cross entropy error, which is between these yes no outputs and these probabilities. So on the one hand, the targets are like yes no or 0 1, while the predictions are probabilities in the range of 0 to 1, something like 0.3, 0.7, 0.9. And the optimization method may also differ, but all of these parts remain the same. So that's logistic regression, and that's all we'll say about it right now, because we want to focus on how to build good logistic regression models. So if you do want to check out internally how all of this works, you should once again check out this YouTube playlist. It is about 1 hour long. It will go into the mathematics and also show you a more geometric interpretation. And as to why it is called logistic regression, because it's solving a classification problem, so it's a bit confusing, the name. The reason is that the output of this sigmoid function or the sigma function that we have, that is a number between 0 to 1, that is called a logistic. And what we're trying to do is we are trying to fit or regress that logistic to the data. So we are trying to get that value of between 0 to 1 as close to 1 in the cases of inputs which have the output yes, and as close to 0 in the cases of inputs which have the output 0. So in some sense, we have, even though we are working with discrete classes, yes and no, we have created this continuous quantity of the probability, and then we want to fit this probability as close to the desired inputs as possible. So that's why it's called logistic regression. But logistic regression is a classification algorithm. So just keep that in mind. Okay. So that's the machine learning workflow, and that's basically all the theory for today. Maybe if we have time at the end, we may work through an actual logistic regression example with a few inputs. But roughly what you want to understand is that it is a different kind of algorithm which outputs probabilities, and it uses a different error function. But the training process is the same, and it is used for classification. Now, classification and regression are both supervised machine learning problems, because they use labeled data. Machine learning, by labeled data, we mean we have some targets. So for classification, the target is the class that we want to assign to each input, rain or no rain, which we already have in our data set. And similarly for regression, it is the quantity that we want to predict. For example, the medical charges. Both of these are called supervised learning, and you can see supervised learning has classification and regression. But there are certain cases where we do not have any labels, and mostly what we want to do is we want to group data into clusters, and that is called unsupervised learning. So we will also look at unsupervised learning towards the very end of this course. But our primary focus will be on supervised learning, which is classification and regression. Okay. So just to come back to the problem that we are looking at, we will train a logistic regression model using the rain in Australia dataset to predict whether or not it will rain at a location tomorrow using today's data. And this is a binary classification problem because it's a yes/no kind of classification. Okay, so let's start by downloading the data. The dataset is on Kaggle, and there are several ways to download the dataset from Kaggle. For example, you can download the data here by clicking download and then upload it to Colab. Now Colab is running on Google servers. So if you check the files tab here, this is not files from your computer. So if you want to take files from your computer, put it on Colab, then you need to use the upload button to do it. So you could download the file here, the zip file, and then you could upload it to Google Colab. And then you'll have to figure out a way to unzip it. It's a bit cumbersome. Another thing you could do is Kaggle has an API, and you can check it out here. So you can use this Kaggle API. This is a command line tool for downloading datasets from Kaggle. So it looks something like this. You say Kaggle datasets download, and you have to run this on the terminal, and you have to put a API key somewhere. So that's a bit cumbersome as well. The approach that we recommend is using the Open Datasets library. So this is an open source library that we have created to make it really easy to download Kaggle datasets anywhere. So you install the Open Datasets library using pip install Open Datasets. Then you import Open Datasets as OD, and then we can check the version of the library, which is 0.1.20. So always make sure you have the latest version, which you can ensure by running -- upgrade. So we've imported Open Datasets as OD, and then we take the dataset URL, which is this URL, the Kaggle page URL, and we run od.download the dataset URL. So let's run that. Now, when you run od.download dataset URL, you will be asked to provide your Kaggle username and a Kaggle API key. Now, where do you find that? The way to do that is click on this, go back to Kaggle. So go to kaggle.com and make sure that you sign in on kaggle.com, and then click on your username, then click on account. And here you should see an option, create new API token. So just click create new API token, and that is going to download this file called kaggle.json to your computer. Now this file kaggle.json contains the information that you need. So if you open up kaggle.json, as you have opened it up here, as we've opened it up here, you can take the username. So let me take the username. I'm going to put it here. And then you will need to provide your Kaggle key. So I'm going to take my Kaggle key, put it in here as well, and hit enter. And now I am authenticated and this dataset has been downloaded. Okay, you can verify that this dataset is downloaded by opening up the files tab and checking here that you have the name of the dataset here. Another way you can do this, instead of having to manually enter your Kaggle key, is to click this upload button and just upload the kaggle.json file here. And once you do that, you will see that your Kaggle credentials are picked up automatically. Okay. And Open Datasets is smart, so it also checks whether you have downloaded the dataset already. So if it has found that you have downloaded the dataset already, it is going to skip the download. So you can specify force equals true if you want to force it to download, or if you want to force it to re-download the dataset, as it has done in this case. Okay, but otherwise it will just detect and it will skip. All right, so now we have this folder, weather dataset rattle package, downloaded from Kaggle using the Open Datasets library. All we need to do is import Open Datasets as OD and run od.download, provide our Kaggle credentials. So let's check this folder, weather dataset rattle package. This is what it's called. So we check it using os.listdir, and then it seems like there's a single file, weather aus.csv. So let's create the full path to this file. So now we have in train CSV the variable. We have the full path to the file, weather dataset rattle package / weather aus.csv. We can now load the data from weather aus.csv using pandas. Now pandas, as you already know, is a library for working with CSV files. So I'm just going to clear my notebook outputs at the moment, just so that we can get all the outputs from scratch. So I just did edit, clear all outputs to remove the previous outputs from my previous execution. Anyway, so now we have PD, pandas imported as PD, and we give it the path to the file that we have just downloaded, and that creates this data frame. So here is now our data set available to us as a data frame. We have information like the date, we have location, we have minimum temperature, maximum temperature, rainfall, evaporation, sunshine, wind direction, etc., etc. So there are a total of 20, I believe there are a total of 23 columns starting from the date. So if you ignore the date for a moment, because we're not going to use date for prediction, and then the final column is the target, the final column is what we want to predict, which is the rain tomorrow column. So we have 23 minus 2, 21 pieces of information or 21 columns of data that we are going to use to make the prediction for whether it will rain tomorrow. So we're looking at 21 weather features for today, and hopefully that should give us enough information to predict whether it will rain tomorrow. Okay. And the dataset contains over 145,000 rows. So the dataset contains a date. It contains some numeric columns. You can see here, these are numeric columns. It also seems to contain some categorical columns. You can see that the wind direction is definitely a categorical column. You can see these are strings, but you can see that there are a limited number of values that these take. So it's a good mix, and our objective is to create a model to predict the value in the column rain tomorrow using all the other columns, maybe except the date. So let's check the data types and see if there are any missing values in these columns. So in total, we have 145,460 rows of data. The date is not, so there are no null values for date. There are no null values for location. That's great, because all of this information was collected on a particular date at a particular location. But you will start to see that there seem to be quite a few null values in the other columns. And that's perfectly fine. Maybe that data was not available. Maybe that data was not measured. Maybe it was not entered. A lot of things could have happened. But one issue here is that the rain today and rain tomorrow columns also seem to have quite a few null values. In fact, you have 145,000 total entries, and here you have 142,000 values for rain today and rain tomorrow. So about 3,000 rows don't seem to have information of whether it rained tomorrow. Now that's a problem, because we want to train a model to predict whether it will rain tomorrow. So we can only use data which contains information on whether it rained tomorrow or not. I mean, if your data itself contains null values in the target column, that's not very useful for the model to learn anything, because you're not giving the model any information. So that's one issue. So we should probably remove the rows where the target column is empty. Now I want to go one step further and say that, and this is just a hypothesis now, that whether it rains today should have a very strong bearing on whether it rains tomorrow, right? So if we have missing data on whether it rains today, I think that a lot of important information is missing here in that data, even though we have a bunch of other information. So what we are going to do is we are going to drop all the rows where either rain today or rain tomorrow are null. Okay, where either the rain today value or the rain tomorrow value are empty. And the second one, it makes sense because it's a target column and we should only have rows where we actually have a value to predict for the target column. But the first one, rain today, I'm just taking a guess here saying that, hey, if I don't know whether it rained today, it's going to be very hard to predict if it rained tomorrow. Okay, so I'm going to just run raw.df.drop NA, rain today and rain tomorrow in place. So from raw.df, we are going to drop this information. And now if you check raw.df dot info, you should see that the number of rows should have gone down. It has gone down to 140,000. But at the same time, we don't have any non-null values anymore. Okay. The rest of them, we will deal with them over time, but these were just two important ones that I felt in this data set we have to take care. And this is something you will also have to figure out on a case by case basis. Are there missing targets? Then maybe those rows are not useful. And are there any critical columns that you should not have null? So maybe you should drop those rows as well. Okay. And you can think about how you will deal with missing values in the other columns, but we will come back to it as well. Okay. Next up, we have some exploratory data analysis and visualization. So before training a machine learning model, it's always a good idea to explore the distributions of the various columns and see how they are related to the target column. And they will often give you a lot of interesting insights about the data. They will give you ideas for whether you need to transform certain features, whether maybe there is some invalid data that you need to fix, whether you can combine multiple features to create new features, whether you can maybe do a logarithm of a certain feature to get a better correlation, etc., etc. There are many ideas that you will get as you explore the data. But today, because our focus is on logistic regression, we'll do a limited amount of EDA. So let's just install these libraries, these plotting libraries, matplotlib, seaborn, and plotly. And first of all, I'm just going to look at the location data. I'm going to see what different locations we have and how many measurements we have across locations. So I believe we have around 29 locations, if I'm not wrong. Let's check that. So rawdf.nunique, that will tell you how many locations we have. rawdf.location.nunique will tell us that, okay, we have 49 locations. So these are the 49 locations. Maybe there are a few more, but for these locations, you can see for each location, we have about 3000 values, roughly speaking. And that makes sense. 10 years of data. So per location, 300 or 360 days of data. Maybe it's not 10, maybe it's 9.5 years. So 300 rows of 360 days of data per year multiplied by about 9 years or 9.5 years should give us about 3000 values. But you will see that for certain locations, the number of measurements is smaller. Maybe they did not have weather stations earlier, they got weather stations recently, or maybe just data was not collected or was lost for certain days. So that's what this tells us. We're getting a good sense that we have mostly uniform distribution of data across locations. I have also chosen color as rain today. So we have split these bars to show whether the value of rain today is no or yes. So if you roughly look at this, you can see that in Albury, there were 2300 rain today, 2300 measurements where there was no rain on those days. And there were 600 days where there was rain on those days. So 600 out of 30,000, out of 3,000, that's about 20% of days. And that seems to be roughly the case, that about 20% of days in pretty much every city, there was rain. And then for about 80 or 75% of days, there was no rain. Of course, that's not true everywhere. For example, here with Uluru, you can see that there are very few days where there was rain. And there are other, like Hobart, where in this case, you can see that there are quite a few days where there was rain. Or I guess this is Walpole. Yeah, on Walpole, there are quite a few days where there was rain. Almost 1,000 out of 2,500. Okay. So location definitely seems to be a factor that decides how much rain there is going to be. So there is some correlation here for sure. Let's look at a few more and we'll go through them very quickly. Let's look at the temperature at 3 p.m. So we're going to plot a histogram of what the temperatures at 3 p.m. look like. And let's also break those histograms by whether it has rained on the next day or not. So my guess is that if the temperature at 3 p.m. today was low, then it's likely that it might rain tomorrow. And this histogram seems to validate that. Like if we just look at the overall histogram, it seems to form a Gaussian curve or a normal distribution. But you can see that the red indicates the cases where it did rain tomorrow. So you can see that there are more cases of low temperatures and rain tomorrow than there are with high temperatures and rain tomorrow. So if the temperature is lower, it seems more likely that it would rain. Although there are still a decent number of examples where the temperature has been high and it has still rained, right? So this is how you can break down histograms specifically for classification problems. You can use this color argument in I'm using Plotly here, but you can, or Plotly Express, but you can use Seaborn, and there you have the hue argument. So you can use the color argument to distinguish between classes. And here I'm just getting a sense that when the temperature is lower, the chances of rainfall might be higher. Maybe let's also look at rain today. Let's also look at the distribution of rain tomorrow. In how many cases is rain tomorrow set to yes? In how many cases is it set to no? So it seems like out of 140,000 data points, for about 110,000 data points, it seems like it did not rain. And then for about the remaining 30,000 data points, it seems like it did rain on the next day, right? So this is called class imbalance. You have two classes, no and yes, and you do not have an equal number of observations in each class. This is an important factor we'll talk about later when we build our models. One other thing we have done here is we have chosen rain today as the color. So what does that tell us? This tells us that there were 92,000 instances where rain today was no and rain tomorrow was also no. And there were only 16,000 instances where rain today was yes and rain tomorrow was no. So that means if it did not rain today, then there's a pretty good chance that it will not rain tomorrow. On the other hand, here you see a mostly even split, which means that if it did rain today, if rain today was yes, it may or may not rain tomorrow. And if rain today was no, again, it may or may not rain tomorrow, right? So predicting rain tomorrow yes is difficult, but predicting rain tomorrow no is easier when rain today is no. Okay, so there are many ways to think about and interpret this chart. So spend some time on each chart trying to understand what it represents. But as such, we can already tell that if it did not rain today, we can be confident that it is not going to rain tomorrow. Of course, there are a lot of other factors involved as well. Then here's a scatter plot of maximum temperature and minimum temperature. So you can see on most days, this is what the distribution of maximum temperature, minimum temperature looks like. In fact, between them, there is a linear correlation. So you could probably even try a linear regression model to predict maximum temperature using minimum temperature, and you would have a line like this. But that's not what we're doing here. What we've done is we've colored in these days or these points using rain today. And you will start to see that the cases where the minimum temperature and the maximum temperatures are very close, right? Or where, first of all, the minimum temperature is low, and second, the maximum temperature is close to the minimum temperature, where there's not a lot of variation. In those days, rain today seems to be more common. So when it rains on a particular day, then the variation in temperature is small. And maybe that is also relevant for whether it rains tomorrow or not, right? So these are all different facets that you can explore about weather. Weather is infinitely complex, and weather has a lot of different interesting things that you can learn from. And then here is a graph of temperature today versus humidity today and how that relates to whether it rains tomorrow. So I'm guessing that if the temperature today is low and the humidity is high, then there's a high chance that there may be rain tomorrow. And that seems to be the case. You can see here that if all the red points are in the low temperature, high humidity region, and the blue points are in the high temperature, low humidity region. Okay. So try and make your own interpretations from these charts and try and visualize all the other columns of the dataset and then study their relation with rain today and rain tomorrow as well. But we will move ahead. So at this point, let us just save our work. So from time to time, you should be saving your work, and you can do this by importing the Jovian Python library and running jovian.commit. And the reason you should do this is because if you step away from the Google Colab notebook for 10 or 15 seconds, then the notebook will shut down and you can lose your work. So when you run jovian.commit, you will be asked to provide an API key. So this is not the Kaggle API key. This is a Jovian API key because we want to take a snapshot of this notebook and put it on Jovian. So you just open up jovian.ai, and in the Get Started tab of your profile, you will be able to find this API key. So just click on API key, come back here and paste it in. And what this will do now is this will capture a snapshot of all the code execution that we have done so far and take that Jupyter notebook and put it on your Jovian profile. So as you can see here, this is my personal copy of the lesson notebook that I've been working on so far, and any changes that you've made will be preserved here. And you can always go back to jovian.ai and you can find it in the notebooks tab of your profile. As you can see here, Python sklearn logistic regression. I have a notebook here just for this. And if you want, you can go back and you can click run on Colab or run on Binder to run this notebook. Okay, so do keep running jovian.commit from time to time. All right. Now, there is one other optional step that I would like to suggest when you're working with massive data sets where you have millions of rows. We don't have it right now. We have 100,000 rows. That's fairly small, relatively speaking. But if you have millions of rows or tens of millions of rows, it's always a good idea to initially work with a sample. And by a sample, we mean a fraction, a randomly picked fraction. And this is so that you can quickly set up your model training notebook so that each line of code that you execute runs quickly and you're able to just try out many different ideas very quickly. So if you would like to work with a sample in this notebook, just set use sample equals true. So let's say if we set use samples equals true, and then we pick a fraction of the data that we want to work with, then all we are doing here is we are setting raw df, the data frame that we have created, to a sample of the data frame. So we are setting raw df to raw df dot sample, and we have the fraction sample fraction dot copy. So we are basically taking a 10% fraction, and instead of using 140,000 rows, we would just be using 14,000 rows, and that will make our training or our analysis much faster. In this case, not by so much, but if we had like 10 million rows, then it would make a lot of sense to maybe just work with 100,000 initially, set up the notebook, and then come back and change use sample back to false. And if it's false, then we won't pick a sample, and then rerun the notebook from top to bottom. Okay, this will save you a lot of time when you're working with massive data sets. So always set up these three lines of code: use sample, sample fraction, and this if else condition, which you can easily switch between having a sample and working with the entire data. So that's a quick trick there. All right, so moving right ahead. Before we train the model, we have to learn a few best practices. So we are going to learn a few best practices that now you will start to see coming up over and over again with every model we build. Now, while building real-world machine learning models, it is quite common to split a dataset into three parts. The first part is the training set, and the training set is used to train the model, which means that we take the inputs from the training set, put them into the model, which is randomly initialized with some random weights. We then take the outputs or the predictions of that model, compare them with the targets, the actual targets, and compute a loss using a loss function. And then we put them through the optimizer to change the model's weights using an optimization technique. So that's machine learning. That's a machine learning training workflow. The training set is used to train the model. But remember that your model is not going to be used on the training data. The training data in this case, for example, is historical data, but we want to use the model on new data. So it will not be accurate to report the model's performance on just the training set. And that is why we create two other sets. We create a validation set and a test set. Now, a validation set is used to evaluate the model during training, because training is often not a one-step process. Often you train a little bit and then see if you got a good enough result, maybe train some more, maybe you change some parameters in the model. Maybe instead of using a logistic regression model, you use a polynomial logistic regression model, or maybe you change the optimization algorithm. Maybe you change from least squares to gradient descent to bilinear solver, etc., right? So while you're training the model, you will want to experiment with a lot of different tweaks to the model structure itself and to the optimization process itself, or maybe even to the loss function. You can even change the loss function. So as you want to tune all of these different ways of training the model, you should be using what is called a validation set, which is simply a fraction of the data set. And you shouldn't use it to train the model, but you should use it to evaluate the model, which means that once you have trained the model using the training set, you then make some predictions on the validation set and simply check what the score on the validation set is. So instead of now using that score to once again train the model or improve the weights, you don't do that. You use just a training set for training, and you use the validation set simply for checking how well the model is doing while you are still experimenting with the model. And picking a good validation set is an essential, a very essential, probably one of the most important parts of a machine learning project. because you want your model to generalize well. And you can learn more about it here. I've linked to a blog about picking good validation sets. And then finally, there is a test set. So then there is a third set, and this test set is used to compare different models or compare different approaches by different people. For example, you have certain data sets which are public data sets that are used by researchers around the world. Now, with these data sets, if everybody reports their accuracies or their performance on a different validation set, maybe somebody picks the first 10% of data, somebody picks the last 10% of data, somebody picks the middle 10% or a random 10%, then those results will not be comparable. So that's why typically it's a common practice to standardize a test set for a data set. And you will often see that you will get a training data and then you will get a test data. So when you have training data, you split it into training and validation. But the test data is what is standardized, and you're not supposed to use it for training. You're not even supposed to use it for validation. You should only use it at the end to report the model's final accuracy. And for many data sets, test sets are provided separately. And then in a lot of cases, for example, in Kaggle data science competitions, you are not given the actual targets for the test set. So you are simply given the inputs for the test set, and you have to then make some predictions for the test set, create a CSV file with your predictions, submit it to Kaggle, and then Kaggle will compare them with the actual data for the test set and then give you the result or give you the score. So this is called a hidden test set. And a lot of companies tend to do this as well. As a data scientist, when you're given a project, you will not be given the entire data. So you'll be given maybe 80% of the data with labels, and then you will be given another 20% of the data with the labels hidden from you. So you will then, once you train all your models, you will take that 20% of data and you will make predictions, give it back to whoever has given you the project, and they will tell you how well your model is doing in the real world. Okay. So it's a very important piece of machine learning, and you will often see when you start out with machine learning that the models that you train perform really well in training. You get to like 98, 99, 100% accuracy. But when you put them out into the real world, they get like 30, 40% accuracy. And this phenomenon is called overfitting, where your model is optimizing too much for the training set. So to give you an analogy to think about the training, validation, and test set, think about how school works or how high school works. So now in India, we have 12 grades, and in grade 12, what happens is you have a textbook and you have classes. So you read the textbook, and in the textbook, for example, for a maths course, in the textbook, you have some questions. So now you solve the questions in the textbook and you use that to improve your understanding of mathematics. And one way to do it is to actually learn the concepts, but the other way to do it is to simply memorize the answers, right? And your model, because you are simply trying to optimize for the lowest possible loss, your model over time will start memorizing training examples. Just like in a lot of school systems, people start memorizing answers to questions. So to avoid blind memorization, what people tend to do is schools conduct exams. So schools conduct a midterm, schools conduct quizzes. So they conduct exams at various places during the school year. And you can think of that as the validation set. So that is where the model or you face questions that you have not already solved. And obviously your performance is a little bit worse, but more importantly, you need to learn the actual concepts or the underlying relationships rather than simply memorizing answers, right? So that's a validation set. But then you have these board exams, or what you might call the SATs, which are used to compare the performances of students across the nation or across the world even. So you can think of that as the test set. So that is like at the very end of your school year, you have to give this one exam, and everybody in the country will be ranked based on that exam. So that's the training set, validation set, and test set. Training set is what you use to learn. Validation set is what you use to improve yourself and change your approach while you're still building a model. And the test set is to report your final performance. Okay. And as a general rule of thumb, this is not set in stone, but as a general rule of thumb, you can use about 60% of the data for training. You can use about 20% data for validation and 20% for test. And this is typically good enough if you're working with let's say tens of thousands of rows or hundreds of thousands. If you have more data, millions of rows, then you can shrink the size of your validation and test sets and use more for training. If you have less data, then you may have to even keep a larger fraction but it really depends on problem to problem. And if a separate test set is already provided to you, let's say you're given a training set and a test set separately, then you can do a training validation split, which could be like a 75-25 or a 70-30 split. So typically this pick or this division of the validation and test set is done randomly, especially when the dataset does not have any inherent order. So if you have just random datasets or random rows in the data, it is very common practice to just pick a random subset of rows for creating the test set and the validation set. And this can be done using the train test split utility from scikit-learn. So we import from scikit-learn.model selection train test split, and you give train test split the data that you want to split. So in this case, we want to split the raw DF, the entire data set that we have. And we want to extract out first 20% and set that aside as the test DF. So as the test data frame. So I'm just setting test size equals 20%. Now, which 20% do we want to extract? So we can specify a random number, and we don't have to. If we don't, then it will pick something automatically, but we can specify a random number. So in this case, I'm just specifying the number 42. And what this will do is this will initialize a random number generator, and then using that random number generator, certain rows will be picked. So a certain fraction of 20% fraction of the data will be put into test DF, and the remaining will be put into what I'm calling train val DF. Okay. Now the benefit of random state is that it gives you the guarantee that every time you pass 42 as the random state, the same fraction, the same 20% fraction will get picked as a test set. So the benefit here is that each time you rerun the notebook, your test and validation sets will not change. So we want a random fraction, which is picked randomly once, but we also want it to be fixed across our runs, because otherwise we will not be able to compare with each run of our notebook whether we're doing better or not, right? So you want to pick a random fraction, but we want to fix it, and that's what random state is for. Okay, so now we've created a test data frame, which is 20% of data, and then we have a training validation data frame, which is the 80% of the data. Now out of the 80, I once again want to do a 20-60 split, which means 25% of the remaining data becomes validation data, and then 20%, 80%, 75% of the remaining data becomes the training data. So I'm using train test split once again, and this time I'm setting the test set to 0.25, and I can use a different random state, but if I want, but it's okay. I'm just using 42 again here, and that's going to give me a training data frame and a validation data frame. So first we extracted a test data frame, then we extracted a validation data frame, and finally we were left with the training data frame. So this is how we have created 3 data frames, and you can check their sizes. Training data frame now contains 84,500 data points. Validation data frame contains 28,000. Test contains 28,000. Okay. So this is what you will do for most data sets. You will pick a random sample as a validation set and a random sample as a test set. If you're given a test set already, this will go away. Maybe you'll have a separate CSV file for test. So you'll simply do a 75-25 split between training and validation. Okay. Now, one other thing I want to add here is when you're working with dates, which we are in this case, fortunately or unfortunately. So when you're working with dates, there is an additional consideration to keep in mind, because we want to take this model which has been trained on historical data, and then we want to use it in the future. Okay. So that means that your model ideally, when it is making prediction on a certain date, it should not have seen any data that came after that date, right? Because you should not train your model to learn from future data to predict past data. So whenever you're working with, this is called time series data, or whenever you're working with dates, it is often a better idea to separate training, validation, and test sets with time. So what you want to do is, maybe if we just check out the years in the data, so we have, this is what the distribution of the data looks like. We have these many, we have a bunch of values for 2007, a bunch of them for 2008, 9, 10, 11, 12, 13, 14. And we are presumably going to use the model to make predictions in 2018 or 2019. So here is a good way to divide the training and validation and test sets. How about we take the data till 2014 as the training set. So we train the model using data till 2014. Then we use the data from 2015 as the validation set. So now the model will be evaluated on data from the future, data it has not already seen in the past, right? So we use 2015 as the validation set, and then we use 2016 and 2017 as the test set. So our final accuracy of the model will be reported by its performance on 2016 and 2017, while the model has been trained and evaluated on data till 2014 and 2015. The benefit of this is that because we are going to use the model in 2018 and 2019, so the test set's score is going to very well reflect how the model will perform in real life. On the other hand, let's say if you pick 2011 as the test set, then it's possible that the model may use some information from 2010 and 2012 to become a better predictor for 2011 than it would be for 2018, right? Because it has access to data from the past as well as the future. So what I want you to take away from this is whenever you're working with dates or with time series data, it's often a good idea to take the last fraction as the test set and maybe a fraction just before that as the validation set. Okay. So that's what I'm going to do. I have created this year column. So I'm going to convert raw df.date to a date time series, and then I'm going to get the year out of it. And for the training data frame, so I'm going to ignore what I had created earlier, all of these data frames using random splitting. But for the training data frame, I'm just going to use the data before 2015. For the validation data frame, I'm going to use data just from 2015. And from the test data frame, I'm going to use the data after 2015. So 2016 and 17 are going to be the test set, validation is going to be 2015, and training is going to be before 2015. And this is what the split looks like. So it's not a perfect 60-20-20 split, but we have still ensured that the validation and test set both contain data for at least 12 months or an entire calendar year, which means they see all the seasonality and they occur in the future after the training data. So which will more accurately reflect our model's performance in the real world. So the whole purpose of test, training, validation, etc. is to create a model whose performance can be reliably measured on how it will perform in the real world, right? We don't just want to get a higher accuracy just for the sake of reporting it. We want to create models that work well in the real world, and that's why we do all these splits. So that's your training set now. The first 8 years of data, the first seven years of data, then validation set, the next 1 year of data, and then the next year and a half of data is the test set. Okay. If you do not have dates, then pick a random 60-20-20 sample. All right. And I'm just going to save my notebook once again and record another snapshot. Now, some of what we have done here may seem a little complex, it's not something that you may be able to grasp in the first glance, but do work through the notebook, do go through every line of code. All of it is explained, and you can check out, you can separate out each line into a separate cell and try and work through it and see how it works. So next best practice or next step in a machine learning problem is to identify the input and target columns. And often this is something that people tend to mess up as well, just in the hurry to get to the modeling process. So not all columns in a dataset are useful for training a model. In fact, in the current dataset, if we look at raw df, you can see here that we have a date column, and the date column is different for each day. In fact, it only contains dates from 2008 to 2017. Now, presumably we're going to use the model in 2020 or 2021 and onwards. So the date will never be something like this, right? So the model will, so there's no point training the model on these dates or dates which it has seen in the past if it is going to be used in the future, right? So date is not a useful input to the model. On the other hand, minimum temperature definitely is, because the model is going to see temperatures in the same ranges. It may not see 13.4, but it may see 13.5, it may see 13.1. So this is a useful thing to have. Maximum temperature is again a useful thing to have. So all of these rows, apart from date, like location, min temp, max temp, etc., these are definitely useful for prediction. So we definitely want to use these. Similarly, sometimes you will have ID columns. For example, in the last example of insurance or medical charges prediction, there were certain IDs. Sometimes you will have names of people, like you may have names of a customer, or maybe you may have emails of customers, or you may have like a customer ID or some unique identifier, which is different for every row. So whenever you have these ID columns, you should completely ignore those, because those are just unique and that is not useful information to use. Then there is obviously also a target column, the column that we want to predict. We want to take all of this information and we want to use it to predict the rain tomorrow column. So we want to make sure that we don't use the rain tomorrow column as an input. For sure, right? You don't want to use whether it rain tomorrow to predict whether it rain tomorrow. You don't. The rain tomorrow is a target, and that is why, and it seems like an obvious thing, but in a lot of cases you will see that you are training a model and then you train the model and you suddenly see 100% accuracy, 100% training accuracy, 100% validation, 100% test accuracy. And you debug and debug, or maybe you just think you've won, but ultimately you will figure out that you were actually using the target as an input. I do this all the time whenever I'm training models. So that's why one thing you should try and do is very clearly identify what are the inputs to your model and what are the outputs and what are the things you need to ignore. So I'm going to create two lists here. One is a list of input columns. So here I'm saying train df dot columns. So from training data frame or from the raw data frame, doesn't matter. They have the same set of columns. I'm going to pick from column number 1, which means I'm going to ignore the date, and I'm going to pick till the column number n-2. So I'm going to skip the last column, which is the target. So that's going to give me all the columns starting from location to rain today. Okay. And then the target column that I want to predict is rain tomorrow. In this case, there is just one target column, and generally in classification, there is just one target column. But sometimes there might be multiple target columns as well. So this could be target columns in certain cases. And another thing to keep in mind is certain machine learning algorithms expect you to always have a list of target columns. For example, linear regression does expect that, I think, but certain machine learning algorithms work fine with just a single value. So logistic regression, in fact, expects you to have a single target column. And that's why we're just picking a single target column here. Okay. So just be aware of that. Sometimes this may need to be a list. Sometimes this may need to be just a string. Sometimes it wouldn't matter. But this is the idea. We have input columns and target columns. So these are the input columns, just very explicitly printing it out. It's always a good idea to eyeball this and make sure, okay, I'm not using rain tomorrow as the target. And then we have the target column as well, which is rain tomorrow. Now, another special case of this is sometimes you may have columns which are derived from the target column. For example, you may have rain tomorrow and rainfall tomorrow in, let's say, in millimeters. So if you have a column rain tomorrow and you have a column rainfall tomorrow, then you probably don't want to use rainfall tomorrow as an input, because you want to use a model with today's data. So you want to make sure that, and rainfall tomorrow is going to be a very strong indicator of rain tomorrow, but at the same time, it is derived information from rain tomorrow, and it is not something that you will have in the real world. So be mindful of that. Sometimes some of these columns are derived or very closely related to the target and are targets themselves. So make sure to ignore those, right? If you want to use today's data, you pick just today's data. So that's your input columns and target columns. Now, once we have that, it's a good idea to just create separate data frames. So you have train inputs. Here I'm simply picking input columns from the training data frame. And I'm also just creating a copy, because now we'll start modifying this data. We'll start doing scaling and encoding, etc. So I'm just going to create a copy so that the original data is not disturbed. And then we have train target. So here I'm just picking the target column. So here I'm picking columns. So train inputs is going to be a data frame. You can see here, train inputs. It's a data frame containing just the input columns, and then train targets picks single column. So it's going to be a pandas series. You can see that this is a series, and this series has just a bunch of yeses and nos. Similarly, we are creating validation inputs and validation targets. We are creating test inputs and test targets, and we can see what they look like. So these will either, mostly all the inputs are going to be data frames or sometimes NumPy arrays. And then the targets could be series or they could be data frames. And if you're ever in doubt, you can always just check what the type is. So this is a series, but the general rule of thumb is when you're picking multiple columns or a list of columns, that's when you get a data frame. When you pick a single column, you get a series. Okay. One other thing that will be useful is to identify which columns are numerical and which ones are categorical. This will be useful later because we will need to convert categorical data into numerical data for training a logistic regression model or any machine learning model. So if we look here, these seem to be numeric, and then this seems to be categorical. I don't know, maybe this is also numeric, but then this is definitely categorical. This is definitely categorical. This is definitely numeric. So there's a combination. In fact, location here is definitely a categorical column, and it has a grand total of 49 categories. And obviously location is a big factor because the weather or the climate of each location is definitely different. So as long as we are predicting just for these same locations, location is an important factor to look at. And by the way, you should also now understand that because we are using location as an input, your model can only make predictions for locations that it has already seen. Now, if you use this you cannot use this model for New York because your model does not know what to do with New York as an input. It has only seen a location as an input. So if you want to create something generic, something that works irrespective of location, then you will have to remove the location column, right? So keep that in mind. On a case-by-case basis, you'll have to figure out whether to use it or not. For now, we'll assume that we are going to use the model for predicting these same locations most of the time. So we will retain the location column. So here's a quick trick to come up with numerical and categorical columns. So if you take a data frame and then call select D types and simply give it which type of columns to include. So here we have said include np.number, and then you can get the list of columns. So basically this selects just those columns of data in the data frame where they are numeric, and dot columns gives you the name of the numeric columns. And then we're just converting them to a list. So I think we should remove this as well. And that should give us the numeric columns. So let's see, numeric calls. So these are all the numeric calls: minimum temperature, maximum temperature, rainfall, evaporation, sunshine, etc. Okay. All I've done is I've selected the columns which have a numeric type np.number, and I've taken the list of that columns and I've converted it into a list. And similarly for categorical, we have selected the list of columns with data type object, and we've converted those to list. Now I was able to do this because there are no string columns in this data set, but if there were string columns, then we would have to do something more interesting, or maybe we would have to manually type out categorical columns. And you can, by the way, you can do that as well. That's completely fine. There are just 23 columns, so you can manually type out the names of numeric and categorical columns. Okay. So that's numeric and categorical columns. Here's numeric columns: min, temp, max temp, rainfall, etc. And as soon as you have numeric columns, you can also very quickly check some statistics by calling .describe. So here we are just selecting the numeric columns from the training inputs, and then we are calling .describe just to explore, okay, what does the ranges of these values look like? What's the minimum? What's the maximum? What's the standard deviation? What's the median? So it seems like minimum temperature can go up to -8 and maximum temperature can go up to, so the minimum temperature can go from -8.5 to 33, and the maximum temperature goes from -4 to 48. And this is also a good opportunity for you to see if there are any values that don't make any sense at all, in which case we may have to maybe do some, fix some incorrect values in some way, maybe draw some more histograms, etc. Okay. Yep, but these values look fine to me, so I don't think there's a lot of data cleaning required here at this point. So that's the numeric data. And let's also check the categorical data. For the categorical data, it's a good idea to check how many unique categories there are. And this will also let you verify if all these are actually categorical. For example, location, there are 49 values. That may seem like a lot, but we are dealing with 140,000 rows of data here. So 50 is still, I think I would still call it categorical. I would not call it a string. But if I had maybe a 5,000 or 10,000 different values, then maybe that's better suited as a string column and not a categorical column. Then we have wind direction. We have 16 values for those. Well, that's just simple directions, and wind direction at 9 a.m., 3 p.m. And finally, we have the rain today column, which is also a categorical column. Yes and no. And rain today, I'm sure, is going to be very helpful in predicting whether it's going to rain the next day or not. Okay. So that's just identifying the input columns, target columns, and within the input columns, the numeric columns and categorical columns. And the reason we've done this is because we'll now start doing some processing with this data. Now, machine learning models cannot work with missing data. Whenever you have a NAN and you try to train a machine learning model, it's probably going to crash. So you need to fill these missing values with some valid values. And the process of filling missing values is called imputation. Now, there are several techniques for imputation, but we will use the most basic technique here. And I'll let you check out some of the other techniques, and we will try out some other techniques over time. But the most basic technique is to replace missing values with the average value in the column. And you can do this using the simple imputer class from sklearn.impute. So what we want to do is we want to replace this nan with the average value in this column. And I think the average in this column, if we have just 3 rows, is 17 plus 5, 22 by 2, 11. So we have 11 here, and the average in this column is 6. So we have 6 here. The average in this column is just 7. So we'll just put 7 here. So this is just a guess. It's obviously may not be correct, but you have a choice here. You can either throw away those rows, but if you have a lot of nan values in a certain column and you throw away those rows, you may lose a lot of data. So you just take a guess there, and you think that, okay, maybe I replace it with the average. Sometimes you may choose to replace it with not the average, but maybe a fixed value, and it can do that as well. Simple imputer has several strategies. Sometimes you may replace it by the mean, by the median, if you think that there are outliers that may affect the average. For example, if you have an income column, it's always a good idea to replace it with the median rather than the mean, because there will be outliers that may affect the average. Okay, so many different strategies. We are going to use a simple strategy of filling in nan values with the average value in that column. So how do we do it? We import simple imputer, and then we create the simple imputer object with some parameters, in this case with just a strategy. But you can check what other parameters it supports simply by typing simple imputer and a question mark before that. So here you can see that this is all the help available for simple imputer. You will also see some examples. Missing value, you can also specify what the missing value looks like. In this case, it's np.nan, that's automatic. You can specify what strategy you want to use, and so on. Okay, so we create the imputer. Fine, now we've created an imputer object. So first, before we perform any imputation, let us just check how many missing values we have in each numeric column, so that we can verify later that those were filled. So if we just do on the raw df, which is the entire data, get the numeric columns and check is NA, which is replace each value in the data frame with a true or false, whether or not it is null, and then take the sum. So all of this business is just to count the number of missing values in each column. You can see that min temp, max temp have a low number of missing values. Evaporation, sunshine have a fairly high number. Evaporation, it seems like almost half of the data is missing. On the other hand, we have, for some of these other things, there is a reasonable fraction of missing values. Okay. And here, this is the entire data set, but we could also check these individually for the training, validation, and test sets. For example, here is the check for just train inputs, checking missing values just for the training data. And you will see a similar pattern or similar fraction in the validation and test set as well. Okay. So with that out of the way, the first step in imputation is to fit the imputer to the data, which means that we give it the data that we want to fill, and it's going to look through the columns. It's going to look through all the columns. So it's going to look through the min temp, max temp, rainfall column in the data frame raw df numeric calls, which is just the numeric columns chosen from the raw data frame. So this, and it's going to go through each column, and for each column, it is going to figure out the statistic that you've asked it to figure out, the imputing statistic. In this case, we're using the mean or the average. So it's going to compute the mean for min temp, mean for max temp, mean for rainfall, mean for evaporation, and so on. Okay. So let's call imputer.fit. So it's not yet changed any of the data. We've not filled anything in. We have simply calculated the statistics. So if you now check imputer.statistics underscore. So for the first row, or for the first column that we gave it, and remember, these columns are simply the numeric columns that we have picked. So for the min temp column, it has figured out that the average is 12. For the max temp column, the average is 23. For the rainfall, the average is 2.5. Evaporation, average is 5.4, etc. We have asked it to compute averages. It has computed averages. Now, once these averages have been computed, then they need to be filled into the test set, into the validation set, and into the training set. So here's how we do it. We say imputer.transform. Let's take it step by step. So let's look at train inputs dot numeric calls. Okay. So this is just from my training data, which is the 60% data, just the numeric columns I've picked out in a data frame. And obviously there are a lot of nans here. Then we call imputer. The imputer already knows the averages for all of these columns, min temp, max temp, rainfall, etc. And we call imputer.transform. And it's going to fill all the nans with averages. And now that becomes a NumPy array. So you can't really see here, but if you look at this NumPy array, you will see that it does not contain any nans. So it has looked at all the nans and it has replaced those nans with those average values. Now it's not showing you a data frame because imputer just outputs a NumPy array. But what we can do is we can take this output, this NumPy array, and we can put it back into the data frame as the new values for the numeric columns, right? So we are overwriting the numeric columns now in the original train inputs data frame with the imputed data, which means with the nans replaced with the averages. Okay. And we're doing that for validation data. We are transforming the val inputs numeric calls and overwriting that into val inputs numeric calls and so on. Okay. So all of this business, imputer.transform and then storing the data back, all of this is simply to get to the point where if I now check train inputs numeric calls, you will see that now there are no nan values. Now those nan values have been replaced with the average value, which I guess in this case you can probably tell 5.47 is probably the average value for evaporation. 7.6 is probably the average value for sunshine, but only the nans have been replaced, not all the values. Okay. And now you can check for each of the training, validation and test sets that there are no missing values at all. Okay. Now that's the average imputation technique, but you can try other imputation techniques like median, or sometimes you can also use other columns to impute data. So there are several techniques, just check them out. There's an entire module in scikit-learn that does this. Okay. Now we've dealt with missing values. Another good practice is to scale features to a small range of values. Right now, if you check the numeric features or the numeric columns of data, you will see that they have a fairly wide range. For example, min temperature goes from -8 to 33. On the other hand, wind speed goes from 6 to 135. I think this is min and this is max. Let's see. Yeah, pressure at 3 p.m. Okay, this seems to go all the way up to 1039 and the minimum seems to be 977. Now, what happens is when you put all these numbers into a machine learning algorithm, and you apply weights to them and then you compute a loss function, ultimately the loss is a single number, right? The cross entropy or root mean square loss, etc., etc. The loss is a single number, and we say that higher the loss, worse the model. But what happens is if a certain feature has a very high range of values, maybe like rainfall takes values that are in the thousands, but minimum and maximum temperature take values that are in less than 10, and maybe there's a certain column where the values are 0.00 point something, which are basically in the decimals. So what happens is that the values which have a very high magnitude tend to dominate the loss, because it's ultimately all these numbers getting multiplied and added together. So the values that have a high magnitude, the features that have a high range, tend to dominate the loss, but features that have lower absolute values and features that have lower range of values tend to not show up in the loss as much. So what happens is that if what dominates the loss also dominates the optimization process. So that means the values which have these high numbers are their weights are going to change a lot, but the values which have low numbers or smaller ranges, their weights are not going to change that much during optimization. So just to give everybody a level playing field, just because we measure rainfall in a certain unit where it gets large values, but we measure temperature in a certain unit where it gets lower values. So just to level the playing field for all the features, what we like to do is we should scale all the features into a same range of values. So we're going to scale the features. We're going to scale all the numeric features into the range of values 0 to 1. And sometimes this is also -1 to 1. Either one is fine. It depends on the circumstances, but 0 to 1 is fine for classification problems. And the way you do this is using a min-max scaler. So from sklearn.preprocessing, this is again another module, and in fact, what we're doing right now is called pre-processing. So from sklearn.preprocessing, import min-max scaler, and then you create a min-max scaler, and then you can give it some options. Like you can give it, you can check here, it supports like a feature range, it supports whether it should create a copy of the data, etc., etc. But the objective of the min-max scaler is to identify for each column what is the minimum and what is the maximum, and then scale the values in the column so that they all lie in the range 0 to 1. So it's a two-step process, just like the imputer. First, we fit the scaler to the data. So we compute the range of values for each numeric column. So we say scaler.fit raw df numeric column. So what's happening here is it's going to look at each column from raw df, the entire data frame, min temperature, max temperature, rainfall, evaporation, etc. It's going to look at each column and it's going to find the minimum and maximum of each column when we run scaler.fit. So now we have, if we check the minimum, we can see that the data minimum you can see that for these columns, for the numeric columns, which are min temp, max temp, rainfall, etc., the minimum values are -8.5, -4.8, 0, 0, etc. And then for the maximum values are 33, 48, 375, 371, 145, etc. So now it knows the minimum and the maximum. And this is stored in data min and data max. Now, when we call scaler.transform, what it's going to do is it's going to take this column, and instead of these being in the range minimum to maximum, it is going to scale them in the range 0 to 1. So the minimum value will become 0, the maximum value will become 1, and everything else will be scaled proportionately. So let's do that. It's a pretty simple transformation ultimately. So let's now check train inputs. I think we can just check this here. We can just call describe. You can check for each of the columns now, for each of the numeric columns, you will see that the minimum becomes 0 or very close to 0. You can see all of these are very close to 0. And the maximum becomes 1 or very close to 1. So in this case, you can see that the maximum is 0.56, 0.98. Yeah, it either becomes 1 or very close to 1. In some cases, it may not actually be 1 because of how internally the imputer works. But you can also verify this by looking at the actual data instead of just the statistics. That now all of these values are nice and small. All of these values are between 0 to 1. Okay, all the numerical columns for sure. Okay, so now we have all our numeric data between the range 0 to 1. So none of them will disproportionately affect the loss. And another thing is also that optimization algorithms often use calculus, and calculus involves derivatives and powers of functions and polynomials. So all of these optimization algorithms also work really well when all the numbers are small in the 0 to 1 range. And there are also issues with numerical methods where they cross floating point computation ranges. So if numbers get too large, then decimal information can be lost. And there's a bunch of issues with large numbers, especially when you're working with these numerical optimization methods. So it's always a good idea to get your numbers into a small range. Okay. This one is about categorical data. Now our numerical data is in good shape. Missing values have been filled and the data is in a good 0 to 1 range. Because machine learning models can only be trained with numeric data, we also need to convert categorical data to numbers. So a common technique is to use the one-hot encoding for categorical columns. So you take a categorical column, like a column which has maybe category A, category B, category C. And what you do is you get rid of this column and you instead create a column for each category. So category A becomes a column, cat B becomes a column, cat C becomes a column. And whichever row had the value category A in this categorical column, we put a 1 there in the cat A column and we put zeros in all the other columns. So that's why this is called a one-hot vector. So instead of this category string or this category class, we replace it with a vector which contains a 1 for that particular columns, for that particular categories column, and zeros everywhere else. Similarly, we have category B. This is also one-hot vector. Now this becomes 0, 1, 0, and category C becomes 0, 0, 1. Now here there are only 3 categories, but you can have any number of categories. For example, if we check the number of unique categories, for location we have 49 categories, for wind gust direction we have 16, wind direction 9 AM we have 16, and for rain today we have 2 categories. So now if we want to perform one-hot encoding, what we are actually trying to say is that if I just look at the location data, rawdf.location.unique. What we're actually trying to say is that we want to create one column in the data for Albury, Badgery Creek, Cobar, etc., and put ones and zeros in these columns. So we're going to introduce 49 columns for a location. Now that may seem like a lot, but it's okay. It's not a problem because most of these are just going to be 0, 1, and then most of the time they're going to be zeros, in fact. So it's not something to worry about too much, and our data frame can handle it. So how do we create these one hot encoded columns? The way to do that is using a one hot encoder. Again, from sklearn.preprocessing, import one hot encoder. And I hope you're starting to get the drill now. For all of these pre-processing steps, you create that object. So we are creating a one hot encoder and we are giving it a bunch of options. We are telling it that we don't want to create a sparse matrix. We want to actually create a proper NumPy array. So sparse is just an optimization technique. And we are saying that if you come across a category that you haven't seen before, just ignore it. Okay, then there are several other options that it supports. So we create the encoder object. Then the encoder needs to first understand the data. So we call encoder.fit. And at this point, it's not creating any one hot encodings. It's simply identifying the categories in the data. So okay, so I think this needs to be fixed somehow. I'm just going to check where to fix this. Okay, so we call encoder.fit on rawdf, and maybe there's a way to ignore nan values. Let's see. One hot encoder scikit-learn ignore nan. All right, I'm going to just do a quick fix here. I think this is something to do with the actual version of scikit-learn involved here, but I'm just going to do rawdf dot categorical and pick the categorical calls and dot fill na, and I'm going to just fill it with the word unknown. Okay, yeah, and I'm just going to call it rawdf2. Yeah, so these are some issues that you will run into from time to time. For example, this worked with the version of scikit-learn I had on my computer, but did not run on Colab. And it seems to be, the issue seems to be with nan values. So I'm just going to put in rawdf2 here, which has replaced nan values with the word unknown. And that will just be treated as another category. All right. So now we have called one hot encoder.fit on the raw data frame. So it has looked at all the columns that we gave it, and for each of the columns, it has identified the categories that those columns contain. So if you check categorical calls, the columns of data that we gave to the encoder. So for location, it has identified these categories. And then similarly for wind gust direction, it has identified these categories. And then for rain today, it has identified these categories, no and yes. So for each of the columns in the data frame, so columns location, wind gust, wind direction, 3 p.m. and rain today, it has identified what the list of categories are. Then there is one additional step involved here. We can generate column names for each individual category using this get feature names function. Again, not something you need to remember, something that you can look up. So what we do is now we create a list of category names. So now instead of having just a location, we have location Adelaide, location Albany, location Albury, etc., etc. And similarly going forward, for each category, we have a column name that we've generated, like rain today no and rain today yes. And we just suffix it with the original column's name to avoid any confusion or avoid duplicates in column names. Okay. So like wind direction 3 p.m. has WSW, and similarly wind direction 12 p.m. will also have WSW, or 9 a.m. will also have WSW. Okay. So now we have a list of column names and we are just calling them encoded calls. And we have a list of column names for these new one hot columns that will be created. Finally, to actually create those one hot columns, we call encoder.transform, and then we give it the categorical columns of data. So we are giving train inputs categorical columns, and that is going to give us NumPy arrays. And we want to put those NumPy arrays into the pandas data frame, the train inputs data frame. and with these column names. Okay, so I'll just show you the output here, and okay, I think I will need to fix this as well. So I'm just going to quickly fix train inputs categorical columns dot fill any. Yeah, I think we can just add this. Yeah, so we can just add this here and this should fix it. Sorry about that. Yeah. All right. So what's going to happen here is it is going to transform all those categorical columns and it is going to convert them into these NumPy arrays of one hot encoded vectors, and then it is going to add those as new columns into the data frame. So let's view the test inputs, for example, what that looks like. And you will now see that we have location, min temp, max temp, all of these. But if you start scrolling further, you'll start to see all these new categories, all these new columns: location Adelaide, location Albany, location Albury. So like 49 location columns, and then you will see these, okay, wind gust. So there are 8 wind gust columns, and there are 8 wind direction columns, and then there are 2 rain today columns. Okay, so we have added all these one hot columns, and you can see that there are zeros in most of these and ones every now and then. Every here and there you will see a 1. Like you see what's this location, Albury, so you should see a 1 at Albury. Yeah, you see location Albury is set to 1. Okay, so now we have done some categorical data encoding as well. Again, it's a bunch of code, but ultimately it's something that you can look up quite easily. The more important thing is to just grasp the concept that we are doing this encoding. Now, once you've done all of this pre-processing and before you're ready to train the model, one thing that you should do is you should save these intermediate outputs to disk, because we spent a couple of hours just creating all of this data. And if you're working with really large data sets, it may take even longer because each step will take some time to run, a few seconds to maybe a few minutes, maybe even up to an hour for some of these steps. So now we have these train inputs, train targets, val inputs, val targets, test inputs, test targets for the training and validation and test set. You can save these, and you can save these to CSV, but there are more efficient formats. A very efficient format that Pandas data frame support is called the Parquet format. So you can save these to the Parquet format, and for that you need the PyArrow library installed. So that's why we have this pip install here. So I'm just going to save train inputs to train inputs.parquet. Val inputs I'm going to save to val inputs.parquet, and test inputs I'm going to save to test inputs.parquet. And similarly, I'm also going to save targets. Now there's just one additional step here. We need to convert them into data frames to actually save them properly. So I'm just going to save those targets as well. And now the benefit is the next time you restart this notebook, or maybe you start a new notebook, maybe you want to do pre-processing in one notebook and then you want to do model training in another notebook. You don't need to repeat all these pre-processing steps. You can simply read these files. So I'm just reading in train inputs, val inputs, test inputs, train targets, val targets, test targets, and that can give me the same information. So now what we've just done is we have taken the training, validation, and test sets after all the pre-processing and saved them to the disk, so that if we shut down the Jupyter notebook, it will still be there. Of course, in Colab, the disk also goes away. So this is not completely true. So what you'll want to do is maybe download all these Parquet files, or maybe save them to their Google Drive or something. But at the very least, you want to back up these files if you're working on Colab. And then you can upload them into a new Colab notebook when you're working on the next project, or when you want to use this data, and then you can simply load it up. On your computer, you don't need to do all that business. It is always saved on your file system. So you can write it and read these anytime. Okay. So that's just a quick tip, that whenever you have done a lot of pre-processing, just save the outputs after the pre-processing. And finally, after all of that, we are finally ready to train the logistic regression model. Okay. It may seem like we've done a lot of work, but actually it's just been 3 or 4 steps, which is identifying the inputs and the targets, and identifying numeric and categorical columns, filling missing values in numerical columns, imputing. Yeah, that was through imputation. Then scaling numeric columns to the 0 to 1 range. Then we also replace the categorical columns with one hot vectors. So these are just 4 or 5 pre-processing steps that we've performed. And now we have our data in the form where most of it is numeric data. Like if I check train inputs, Yeah, so we still have these categorical columns which we will probably get rid of while actually training the model. But we have numeric data for the numeric columns, and then the categorical columns have also been converted into numeric data. So now we're ready to train the model. And logistic regression, as I've already mentioned, is a common technique for solving binary classification problems. We take a linear combination or a weighted sum of the input features. That's why we need them all to be numeric, and that's why we also need them all to be in similar ranges so that they don't mess up. One feature does not mess up the loss. Then we take that weighted combination and we apply the sigmoid function, which ultimately gives us a number between 0 to 1 for each input. So for each set of inputs, for each specific row of data, we get a number as between 0 and 1 as the output of the model. The number represents a probability of the input being classified as yes. So that's how we interpret the number from the model. Then we use the cross entropy loss to evaluate how good the probability is with respect to the results. Now, obviously, intuitively what we want is if the target is yes or 1, then we want the probability to be high, very close to 1. If the target is no or 0, then we want the probability to be no. And that's what this formula captures. This is called cross entropy. We won't get into it, but the idea is it penalizes bad predictions. Okay. And then we train it using the normal machine learning training process. So here's how we train a logistic regression model. The actual model training part is so simple that you simply import logistic regression from sklearn.linear model, and then you train logistic regression. Now here, if I hover over it here, you should be able to see that there are a lot of different arguments that we can pass. The kind of penalty, there's something called a dual, something called a C, something called a tolerance, fit, intercept, etc., etc. You can even specify random state. You can provide weights for the different classes. You can specify the number of iterations. So these are all parameters that you can change. And remember, I was talking about the validation set. So each time you try a different kind of model with a different set of parameters, you can use the validation set to judge whether those parameters led to a good result or not. Okay. Now in my case, I have picked this solver called liblinear because, and you can check what kind of solvers it supports. You can just see the options here. Yeah, so there is Newton CG, there is liblinear, there is SAG, SAGA. You can try out different ones. The reason I picked liblinear was because LBFGS did not work for me. Sometimes they're unable to solve the problem because these are numerical methods. Sometimes they just fail to solve the problem. So you try a different solver. So I just tried the liblinear solver, and that took just like half a second. You can see in total, it took just about half a second to perform this entire fit. Well, actually we have not yet created the model. So I'll take that back. So now we've just created this model. We've just instantiated this model with the liblinear solver and with some other options. Now to train the model, we can train the model using model.fit. Okay, so let's run model.fit. And this is going to take a few seconds, maybe. Okay, it took 1.4 seconds on my computer. It took less than that. And what did it just do? Well, it uses this exact machine learning workflow. And I hope you're starting to get bored with this at this point, because that's what we want. You want to get this machine learning workflow in your head internalized. So we initialize the model with some random parameters. So with some random weights and biases, we pick random values for these W's and B's for each of the features that we have. Then we pass the inputs, the training data, into the model, and we get some predictions. We take the predictions and then we take the outputs from the model, and when we run them through a loss function. And then we use an optimization technique to slightly reduce the loss and improve the weights of the model. And in this case, we're using the liblinear optimization technique. Then we repeat the steps 1 to 4 till the predictions from the model are good enough. So if you see here, if I see logistic regression, you will see that there is this max iter. This is the maximum number of iterations that we want the model to take. So here what we are telling the model is that we want to repeat this process of creating predictions, comparing them with the targets, running some optimization 100 times at most. Or we want to stop at a point where the tolerance or where the loss gets lower than a particular value of 0.001, right? So all of these things you can configure. If you want the model to go on for longer, increase max iterations and reduce the value of tolerance, make the tolerance lower. and that way it will go on for longer. It will take more time, but maybe it will learn better. So all of those things are things you can customize in the model. Okay, but that's it. The model has now been fitted. So now for each of the individual columns in the data, or for each of the numeric columns that we have given it, it is going to now have a particular weight. And I just want to tell you one other thing that I've done here. I have not given it the entire training inputs because train inputs contains some categorical data as well. Remember, we have not removed the location column, although we have added those one hot vectors. So if I just put in train inputs, you can see that although we've added one hot vectors at the end, we have not removed these categorical columns. So I've done this small trick here because I know the names of the numeric columns and I know the names of the encoded columns. So I've just picked the encoded and numeric columns and given that as the input to the model. And then in terms of the targets, we've simply given the training targets, which are simply numbers. Actually, training targets are not numbers. Training targets are these yes and no values. And that's fine. So scikit-learn, specifically logistic regression, can work with numeric training targets. It cannot work with numeric categorical data as inputs, but it can work with training targets. What it'll do is the first class that it encounters, it'll automatically convert that to 1 or to 0, and the second class it encounters, it will convert to 1 and so on. Okay. So targets can be categorical, but inputs cannot be categorical. And this differs from model to model, library to library, etc. In any case, we have now fit the model using the training data, just using the training data. Yep. And now all these weights have been set. So if we check the numeric plus encoded columns, and we have all of these columns, we can see what weight has been assigned to each column in that formula by checking the coef argument here, or the coef property. So minimum temperature has been assigned a weight of 0.89. So it seems like minimum temperature has a weight of 0.89 and maximum temperature has a weight of minus 2.8. So it seems like maximum temperature has a negative impact on whether it will rain tomorrow. And that makes sense. If your maximum temperature gets too high, then it's unlikely to rain tomorrow. Then rainfall has a high positive coefficient. And that again makes sense that yes, you should give a high weightage on what the amount of rainfall today is to figure out if it will rain tomorrow. Evaporation again has a positive coefficient. Sunshine has a negative coefficient. So you can see that these models are not just black boxes. You can actually interpret them. What this model has learned is that rainfall is a good predictor and a strong indicator of whether it will rain tomorrow, the amount of rainfall today. On the other hand, the amount of sunshine today is a strong predictor, but in the opposite direction. If you have a high sunshine today, maybe it's not going to rain tomorrow. Again, wind speed, if your wind speed is very high, then that seems to be a very strong predictor. If you have really fast winds today, then it's probably going to rain tomorrow. And then let's keep going. Let's check humidity. So humidity, it seems like humidity is also a predictor. Specifically, humidity at about 5 p.m. is a good predictor. And if you want to see these sort of side by side, you can create a data frame. You can do pd.dataframe. And let's just create column, or let's call this feature. And here, let's just give this numeric columns plus encoded columns. And here, let's put weight. And let's just put the list of weights here. Okay, and we'll see it as a nice table. Maybe let me just check this. Okay, yeah, I think this, I need to just pick 0 here and this should be fine. Yeah, all right, we finally have it. Just sometimes you can see that this coefficient list is actually a 2-dimensional array, not a 1-dimensional array. That led to a problem. In any case, You can now see the different features and the weights for each feature: rainfall, temperature, evaporation, sunshine, etc. I think we can also increase the number of columns that we want to show here. So if you want to show all the 118 columns, we can show that information here too. But roughly, this is how you interpret the model. A higher the weight for a particular feature, the more important it is for the prediction. The lower the weight, the less important it is. The sign indicates whether it is a positively correlated feature or negatively correlated feature. So your logistic regression model is capturing all of this information in the form of weights. And then of course there is that last intercept or bias term that is added at the end, and that is simply a correction for all values being zero. So that's sort of the zero correction. You may try more experiments, and that is something that may take more time. You may try different imputation techniques. You may try different kind of encodings. There are other encodings as well. Does max iter are the realizations of the simulations? Well, so max iter is, you can see here, what we do is we initialize a model, put some inputs, get predictions. We compare the predictions with the targets using the loss function. We optimize the model using an optimization technique. So one optimization does not, like one pass of optimization does not fix the entire model all forever. It simply makes a small changes to the weights that will slightly reduce the loss, because all of these are approximation methods. So you need to repeat this optimization many times to get a fairly optimal model. So that is what max iteration indicates. How many times you repeat this process. Do you visualize the feature weights with bar H? Yes, you could do that. That's a good idea. I haven't done that, but yeah, I could do that. So let's say we do, let's call this weight df. And let's do SNS dot bar plot data equals weight df. On the x-axis, we can have the weight. And on the y-axis, we can have the feature. Yeah, and hopefully that should give us a good, okay, I think we have a lot of features, so I should probably set yeah, something like this should make it easy to visualize. Yep. So you can see the different features here and their weights visualized here. So you can clearly see that pressure at 3 p.m. is a very important factor. Wind gust speed is a very important factor. A low pressure seems to be a higher indicator, and humidity at 3 p.m. is a very strong factor. You could probably even sort these by the importance. So yeah, that was a great suggestion actually. I should have added this before. So you can probably sort these by importance and just pick the top 10 features. So let's do something like this. Sort values by the feature weight and ascending equals false, and just pick the top 10 out of these, and then we won't need this. Yep. So wind gust speed, humidity at 3 p.m, pressure at 9 a.m, rainfall, temperature at 3 p.m, cloud at 3 p.m, minimum temperature. This is the order in which things are important. Seems like wind is the most important factor in predicting whether it will rain tomorrow. Okay, so moving ahead. Next, we want to make some predictions and evaluate the model. Now, we've trained a model, but we ultimately want to use the model. And before we use the model, we want to evaluate it on the training set, test set, and validation set. So let's evaluate the model. Because we want to use just these numeric and encoded columns, I've created these three variables, xtrain, xval, and xtest, which will contain just the numeric data that we can pass directly into the model. So now I'm going to first make a prediction on the training set, get a bunch of predictions, and the way to do that is called model.predict. So when you call model.predict, you give it a set of inputs. You don't give it targets. You simply give it some inputs, and it is going to give you a list of predictions for those inputs. So this is what our model has predicted: no, 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 yes, no, no, etc. And you can check that there are a few yeses here. If I do a list, you will see that there are actually some yeses. It's just that because only about 20% of the data has rainfall. So even your model's predictions, only about 20% of them are going to be yes. Okay, that's a long list. Should probably have limited this in some way. Anyway, so this is the predictions that our model has created. This is the predictions that our model has created: no, no, yes, yes, etc. And these are the actual targets. So this is what we expect to see from our model. So we have some predictions, we have some targets. For each day, the model is predicted yes or no, and we have the actual target yes or no. The simplest way to understand how well it has done is to simply look at the accuracy. And to look at the accuracy simply means we compute the percentage of matching values in train preds and train targets. You see train preds here. So train preds has a bunch of no's and yeses. Train targets has a bunch of no's and yeses. If we compare, we count these. Okay, this is a match, 1 match, 2 match, 3 match, 4 match, 5 match, mismatch. So we count the number of matches, divide that by the total number of days, which is about 144,552. So, or less. So we can do that directly using this accuracy score function. So from sklearn.metrics, we import accuracy score. We call accuracy score. It's going to do a 1-by-1 match between train targets and train predictions. It's going to count the matches, divide by the total number of values. And that gives us an accuracy of 85.1% on the training set. Okay. Now, apart from giving you predictions, the model can also give you probabilities. If instead of calling model.predict, and this is only for logistic regression, if you call model.predict proba, which is predict underscore proba, and give it an input, it is then going to give you probabilities. You can see that now we get 2 values for each input. This is the probability of the class no, and you can check the classes using model.classes. So this is the probability of the class no, and this is the probability of the class yes. So this is the no class and this is the yes class. And these probabilities add up to 1, you will see, for each model. Right, so it's 94% confident about a no. In this case, it is 94% confident about a no. In this case, it is 0.87% confident about a no, and so on. Okay. So your model is giving you a lot of information. Not only is it giving a prediction, it is also giving you a probability of how confident it is about the prediction. So maybe you can also say that there is a 94% chance that it will not rain tomorrow, and there is an 87% chance that it will rain tomorrow, and so on. Okay. So that's predicting using the model, that is predicting probabilities using the model, and finally getting accuracy score, or getting a accuracy score using the model. Now the accuracy score is a good measure to just get an overall idea of how well the model did. But what you can also do is you can also break down this into what's called a confusion matrix. So you can create this kind of a table where you have these actual values, right? So there are possibilities where there was no rain and the value in the actual target was no, but your model predicted yes. So if the actual value was no and the model predicted yes, we call that a true, and the model predicted no. So if the actual value was no and the model predicted no, we call that a true negative, which means it was able to identify a negative correctly, that it will not rain correctly. And similarly, if the actual value is yes and your model predicted yes, we call that a true positive, which means that it is going to rain tomorrow and your model did predict that it is going to rain tomorrow. So we call that a true positive. So these are both cases in which your model has succeeded. These are both the success scenarios. Then there are 2 types of scenarios, error scenarios, and they are called the type 1 error and type 2 error, or false positive and false negative. Once we have false positive, so false positive is when it is not going to rain tomorrow, or the actual value is no, but your model has predicted yes. So model has predicted that yes, it is going to rain tomorrow. And then similarly, here we have a false negative where the actual value is yes, it is going to rain tomorrow, but your model has predicted no. Now, depending on the business case or what you want to use the model for, you may want to very closely look at false positives or false negatives. For example, if you want to use this model to predict whether a baseball game should be hosted tomorrow in the open, then false negatives are a big problem. You may want to avoid false negatives where it is going to rain tomorrow, but your model predicts that it is not going to rain. So if you have a high number of false negatives, that means you are in for a surprise where you get 50,000 people and people are playing baseball and it starts to rain. That's why maybe you want to optimize, you want to reduce the false negatives and you're not just interested in the accuracy. On the other hand, let's say it's a different kind of model which is predicting whether you may have breast cancer. Then at that point, you may want to take a close look at false positives before, let's say, recommending, I don't know, chemotherapy to somebody. You want to make sure that your model, you want to make sure that it is not a false positive. And for that, while training the model, you want to make sure that the number of false positives is low. So in general, depending on the kind of problem, you may want to optimize either for false positives or for false negatives. And how to do that is something that we will discuss in future lessons. But just keep this in mind that this is called the confusion matrix. And again, sklearn gives you a single line of code to create a confusion matrix. Like you just give it some targets and some predictions, and it is going to give you confusion matrix, and it's also going to convert them into percentages. So here what it tells you is among the actual yeses, which means among the actual no's, which means all the days where rainfall was actually supposed to be no, it predicted no in 94% of the cases, and it predicted yes in 5% of the cases. And then here it tells you that among the cases where it was actually going to rain, it predicted no. It predicted that it won't rain in 47% of cases. So that means your model is actually pretty bad. It has a lot of false negatives, and you should probably not use it for deciding whether you should hold a baseball game in the open tomorrow. And it was 52% of the time when it was going to rain, it has predicted, right? So just by looking at this, now 85% accuracy doesn't seem all that good, because it seems like if it is going to rain tomorrow, and really that's what we're all concerned about, whether you should carry your umbrella or not, your model's performance seems to be 50-50 more or less, right? It's a bit more confident than a random guess. It's about 0.52, but it's not that great, right? So if the model says that it's not going to rain tomorrow, I'm probably not that sure if I can, if the model says that, the model said that it's not going to rain tomorrow, I don't know, because if it is going to rain tomorrow, there is still a 47% chance that the model says that it's not going to rain tomorrow, right? So look at these numbers, spend some time looking at this matrix, and what you can do is you can convert this matrix into a nice heat map. This confusion matrix can be converted into a nice heat map, and you can start to interpret this heat map. Dark values means, especially in these negative regions, means that's good. And like bright values here indicate that this is probably a bad area for the model, right? So yeah, that's a confusion matrix. And what we've done is we've simply created this predict and plot function, which can take some inputs and take some targets, and it will generate the predictions for those targets using the model. It will compute the accuracy, it will print the accuracy, it will create a confusion matrix, and it will plot the confusion matrix. Okay. So this is how you analyze the results of a model. So in this case, it has about 85% accuracy on the training set. Let's validate this. Let's check it on the validation set. So now we are running it now we are calling this predict and plot function that we created with the validation data and the validation targets. And on the validation targets as well, we get an accuracy of 85.4%. So that's good. Even on data that the model has not seen before, it is about 85% accurate. That's good. Let's check the test set. Now the test set, remember, is data from the last 2 years or the last 1.5 years. And on the test set, you can see that the accuracy is slightly low. It's about 84.2%. All right. So now you can start to see that how the training and validation and test sets are useful. If the test set accuracy was 30%, that means the model is very badly overfitted to the training data. But since it is quite close, it's about 84% and training is 85%. You can accurately just go back and report to your boss or whoever gave you the project that, hey, my model is about 84% accurate, although it does have a lot of false negatives. So please don't use it to decide if you should do something in the open tomorrow. Okay. Now, one thing you might wonder is how good is 84% accuracy? And while this depends on the nature of the problem and on the business requirements, a good way to verify whether a model has actually learned something useful is to compare its result to a random or a dump model, right? So for example, let's create two models. we'll create a model called random guess, which takes some inputs like the training inputs or validation inputs, and it completely ignores the inputs and it randomly picks yes or no. Okay, so that's my random guess model. And then I'm going to create another model called all no. And this is a model that just says that it's not going to rain. It always says that it's not going to rain. Okay. So now if I use random guess, for example, on the validation set, so if I call random guess on X val, which is the data from the validation set, you see that it half of them are no's and half of them are yeses. And on the other hand, if I use all no on the X, you see that this always returns no. Okay. So these are also models. These may not be very intelligent models. These may not have looked into the data, but these are models. And one thing that you should always try and do is take your brilliant machine learning model that you've created after all this pre-processing, etc., and compare it to a baseline model like this, something like a random guess or an all no. So let's do that. Let's compute the accuracy for the test data or the test set using the random guess model. So we give it the X test that gives us the predictions for the random guess from the random guess model and compare that with targets. So a random guess gives us about a 50% accuracy, and that makes sense because you have two outcomes, and if you just guess randomly 50%, your like any given input, you have a 50% chance of getting it right, roughly, so to speak. But if you were more intelligent and if you were to always say no, then what would you get? Then your model would have a 77% accuracy. And this is because in the data set, remember, there's an imbalance. So on 77% of days, there was no rain, and only on 23% of days there was rain. So just by predicting that there was no rain, your model achieves an accuracy of 77%. Now, thankfully, the model that we have created has an accuracy of 85 or 84%, which is definitely better than 77%. But this is not always the case. And you will often find that once you train a model and do all of this analysis and create all these features and normalization, etc., and after all that, you get a model that's worse than a dumb model like this. Like there are definitely ways in which we could have created a logistic regression model that was maybe 65% accurate. So that means that your model is worse than simply predicting no always, right? So always analyze your models against these dumb or very simplistic baselines and make sure that it makes sense. And now you may say, okay, if 77 is so easy to get, then I don't know if 84% is something that is worth putting all this effort for, right? Another thing to do is maybe do a human baseline. So what you could do is maybe you could pick 1,000 days of data from the test set and ask a meteorologist to predict and check their accuracy, and then check your model's accuracy on those 1,000 data points. And this is called a human baseline. And if your model is able to do better than that particular meteorologist, then you have kind of beaten a human. And that is how we say that this AI is now better than a human. Of course, you don't want to just beat one person. Ideally, you want to beat a panel of experts, all of them who have independently made predictions, and you are beating maybe the average of their predictions. And if you're comprehensively doing that, then at that point, we can probably just tell all the meteorologists to go home because they're not able to do as well as our model is able to do, right? And that brings me to this last piece, which is to make predictions on actual single inputs. Now, once the model has been trained to a satisfactory accuracy, once we have analyzed it, compared it with meteorologists, and we've decided that, okay, we can fire them and just use this model, we now have to use this model to make predictions on new data. So consider this a dictionary containing the data from the Catherine Weather Department today. So 2021-6-19. This is the location, this is the minimum temperature, maximum temperature, rainfall, evaporation, etc., and whether it rained today. We have all the information, but obviously since tomorrow hasn't happened, we don't know if it's going to rain tomorrow, and we have to send out a weather bulletin in a couple of hours. So now it is up to our model to tell us if it is going to rain tomorrow, okay? And as you run through this notebook, you can try changing some of these parameters. So I'm just going to, I'm going to create this dictionary. And let's see how we can use our model to make predictions. Now, obviously we cannot directly feed this dictionary into our model. Our model expects numbers and encoded categorical data, etc., etc. So the best way when you want to make a prediction on a new input is to try and mimic the original input format as closely as possible. So the original input format was a pandas data frame. And this would ideally be a row within a data frame. So here's what we can do. We can take the new input, which is a dictionary, and we can put this into a list. So now we get a list of dictionaries, and remember the pandas data frame constructor can take a list of dictionaries and it interprets each dictionary as a row of data. So we are just going to create a pandas data frame using this list of dictionaries, which contains just one dictionary. So that means the pandas data frame will contain just one row of data. So we've taken this dictionary and converted this into this pandas data frame. Okay. The objective for you is to get the data into the same kind of a structure that was used to train the model. So this was the structure that was used to train the model, right? A pandas data frame. And here we have just one data point. So that's why we have just one row. But let's say if you had this information about all the locations, all the different locations, you had collected 49 pieces of information, you could create a data frame with 49 rows. Okay, in any case, we now have this data frame. Can we pass this into the model? Not yet, because we need to apply the same pre-processing steps that we have applied while training the model. First is imputation of the missing values. And this is where the imputer that we had created earlier is going to be useful. So I'm just going to call imputer.transform. And remember, it's going to use the mean values that it had calculated on the entire data set. So we can't just create a new imputer. We need to use that original imputer. We need to keep that imputer around. And I'll tell you how to keep it around when we talk about saving models. But we say imputer.transform, and then we give it new input df and just the numeric columns. Right? Remember, so we also need to keep a list of the numeric columns, and then we need to grab the numeric columns out of the new input df and transform them. And that will fill any missing data. So for example, there's one nan here for sunshine that will get filled in. Then we have scaling. So numeric features also have to be scaled. Remember these values 23, 22, all of these have to be brought into the 0 to 1 range. So we now say scalar.transform, and that's why the scalar is useful. And remember, the scalar has already been fitted on the entire data set. So it knows the ranges. So we can't create a new scalar. So we use scalar.transform, and then we pass in the numeric columns, and that's going to then give us the new input df now with the numeric value scaled. And finally, we also want to encode the categorical column. So we take the categorical columns, and remember we have an encoder. It already knows what all the different categories are and what all the different columns need to be created are. And it's going to create these encoded columns. And let's check new input df now. Yeah, so now you can see now it has been converted into the format that is ready to be passed into the model. Okay, it's still one row of data. So now let's grab from new input df. Remember, we only want to pass in numbers into the model. So we take numeric columns, we take encoded columns, and we get those from the new input df, and we check x new input. You can see that now it just contains the numbers that can be passed in directly, and all the columns are in exactly the same order. That's also very important, right? All the columns are in exactly the same order that they are in the input. That's why these pre-processing steps should be applied exactly to every new input. And we can now make a prediction. So we call model.predict. Like if we just call model.predict, it's going to give us a list of predictions, one for each row of data. You can see that it's an array of yes, but obviously we just want the first prediction because we just have one row. So that's why we're just selecting 0 here. So we say prediction and we check prediction, and it turns out the prediction is yes. So based on this input, Catherine, min temperature, max temperature, etc., the model has predicted that it will rain tomorrow. And what is the probability? We can check the probability as well. We can get the probability that the model thinks it will rain tomorrow. So the probability for no is 0. The probability for yes is 51%. So it seems like the model is just on the border. It's not 100% sure on whether it will rain tomorrow. It's only about 51% sure. So maybe, I don't know if you should put this out in the weather bulletin that it will rain tomorrow. You may want to say slight chances of rain and leave that possibility open. And that's another interesting thing to look at, right? So now one thing you can play around with is try changing some of these values. Like now that you know that wind speed at 3 p.m. is very important, maybe try changing the wind speed. Maybe let me change this wind speed to 0. Okay. And let me repeat these steps. And let's see if the prediction changes. So the prediction still says yes. Let's see if the probabilities change. Okay, the model actually has become more confident. So I don't know, maybe it's not the 3 p.m. wind speed, I think, but maybe it is just the overall wind speed. I think this is the one actually. So let me just change this to 10 and let me keep the 3 p.m. wind speed at 20. Let's see if that creates a change. And this is how you want to, okay, so now the prediction is no, right? So if you can see that the wind gust speed has gone down by a lot from 52 to 10. You can see that now it is 89% confident that it will not rain tomorrow. So this is how you should interpret your model, and this is how you should also make sense of your model if these things are sensible. You should then sit with the meteorologist or the domain expert and show them, hey, if I put in this number, this is the output that it gives and this is the probability that it gives. Do you think it makes sense? And then they can tell you from weather research if these things actually make sense or not. And if some of these things don't make sense, then maybe you need to go back and check these correlations. And sometimes you may have accidental correlations. Sometimes you may have what is called a data leak, where maybe some information from the target has been put into one of these input columns somehow, and all of these things happen. And that's why models don't work well in real life. So you need to look into the model and see why it is giving you a certain result. And again, as always, it helps to create a helper function to make these predictions. So now we have this helper function predict input, and then we can just make some modifications into this new input, and we can try things out, right? For example, here for this input, I've just changed the location to Lausanton, and it seems like now it is more confident. Maybe if I pick Albury, let me see if the prediction is going to change. Yeah, so now it's even more, it's like 79% confident. Let me pick, there was a certain place, Uluru, which had very little rain. So let me put Uluru here. Okay, it's still confident. So it seems like that this indicates a very strong chance of rain for most places, right? So that's how you analyze your model. You can try changing some of the other parameters. Let me try rainfall here. Let me try the rainfall for today. Let me make it 2. Okay, still says yes. So do play around with this. Maybe pick some random row from the data and then try and change a few things, or maybe even look this information up today live and put in this information and see how useful this model is 3 years from being created. And honestly, climate does not really change that much in just 3 years. It's a multi-decade or multi-century phenomena. So if you've trained a model using data from 2010 to 2017, it should hold up pretty well even today in 2021. So you could go on Yahoo Weather or somewhere or AccuWeather and get all this information and then put this information into the model and check if it actually rains tomorrow by checking it, right? And that is what machine learning is. It is about taking data and using data to make predictions. But how do you make predictions from data? You assume a certain relationship between the inputs, which is the weather information for today, and the output, which is whether it will rain tomorrow. And that relationship is called the model. And that model has some inherent parameters called weights of the model, which are initially randomly initialized. And then you train the model, which means that you make predictions, compare them with the actual data. And that's where you need labeled historical data or labeled data for whether it rained the next day for the last 10 years. And using that comparison, compute a loss, reduce the loss using an optimization technique, make the model's parameters better. And as the model gets better, then you evaluate the model, you interpret the model, and then you use the model in the real world. This is used for weather prediction. This is used for predicting whether somebody will default on a loan. This can be used for predicting if a certain tumor will cause cancer. This can be used for predicting, let's say, well, actually, a similar technique is used for predicting, for recognizing pictures of cats and dogs. Logistic regression. If you check out our other course, which is the deep learning with PyTorch 0 to GANs course, there we apply logistic regression on image data. So a very similar technique is applied to just identify separate pictures of cats and dogs, or even like identify handwritten digits. So it's a very versatile technique, logistic regression by itself, but machine learning in general, it can be applied to a whole bunch of different kind of problems. One last thing I want to cover before we close for the day is saving and loading trained models. Now, obviously, we've spent a lot of time training these models. We've done a bunch of pre-processing. Just as we have saved pre-processed data, we should also save the trained models. And what is the model really? Well, the model is two things. The model is what kind of model it is, which is the logistic regression model, and how it was initialized. So all the parameters that we are given in the initialization, like the kind of optimizer, the number of iterations, etc., etc. And then it is the learned weights of the model, which is what has come out of model.fit. So we should save all of this so that we can reuse this model without having to train it, without having to fit it on this pre-processed data from scratch. In fact, once the model is trained and we know the coefficients, we don't need to look at the data anymore. We can just hand over the coefficients to a software developer and they can set up a simple web page where somebody inputs a bunch of weather parameters, and then that input is sent to a web server where we simply multiply those parameters with the coefficients, apply the sigmoid function, and then return a result. And that is going to just work as a standalone web application without ever looking at all the data. So in some sense, the model's parameters or the model's weights is sort of a condensed or a dense representation of all the intelligence that is present within the data, right? So it is capturing all the patterns within that large data set of 130,000 rows of data into just these 250 numbers, 250 weights and biases. And that is really what makes machine learning so powerful. You are summarizing millions of data points into just these hundreds of numbers, or sometimes maybe 1,000 numbers, but still these very dense representations, which is the sort of the intelligence of the data and can be used to make predictions. So how do we save our model? Now, we can save our model using this library called joblib, but we don't want to just save our model. We want to save our model. We want to save our imputers. We want to save our scalars. We want to save our encoders. We want to save even the column names that are important. Anything that will be required while generating predictions using the model should be saved. So anything that is used inside this function, for example, should be saved. So here's what you can do. Joblib is a very generic library which can save any Python data. So I would typically create a dictionary like this. So I'm calling this AussieRain, the dictionary, and I'm giving it the model, the imputer, the scalar, the encoder, input columns, etc. So I have the key model and I have the value, which is the actual machine learning model that I've created. I have the key imputer and I have the value, which is the actual imputer that I've created. So here I have created this dictionary. And then I'm going to just save this dictionary using joblib.dump. So we say joblib.dump, give it the name of the Python object. You can just save your model if you want. You can save them as separate files, but I just like to keep them all together because they're going to be used together anyway. And you can save it. Now shut down this notebook and maybe create a new notebook and upload this file AussieRain.joblib. By the way, from Colab, you will want to definitely download this file if you want to keep a copy around. And create a new notebook and upload this file AussieRain.joblib and then just do joblib.load. And you can see that is now loaded into this variable AussieRain2. And that will have now all of these things. Like now we can check AussieRain2 model. So this has been loaded from disk. And yeah. So this has been loaded from the disk and you can see that we have got back the logistic regression model. In fact, you can even check its coefficients and make sure that these coefficients are the coefficients that it had learned. I think it's called coef underscore, yeah. So these seem to be the same coefficients that we looked at, 8.9, 3.16, etc. Great, so now we've been able to retrieve our model. We don't need to retrain our model each time. We can probably hand over this joblib file to a software developer, and maybe if we have time, we will also look at how to create a simple web application using a machine learning model. But for now, let's just make some predictions using this model. So testpreds2 is going to be the results of using the AussieRain2 model to make predictions on X test. And then we are computing the accuracy score from test targets. and that gives the 84.2% result, the exact same result as we had before. And it should, of course, because we've saved whatever was there in the model to disk and then loaded it back. So that's how you save and load models. Now, if you want to attach your model with your Jovian notebook, then while running jovian.commit, you can use this outputs argument and give it a list. And in this list, you have aussierain.joblib, right? So you just give it the name of the output files you want to include. And when you run it and create a notebook on Jovian, that notebook will now contain this joblib file in the files tab, as you can see here, aussierain.joblib. Okay, so you can always, whenever you want to download it, you can always download it very easily. Okay, and we've covered a lot of ground in this tutorial. We've covered a lot of different concepts, and you are not expected to become an expert in all of these or even any of these immediately. The things that we've learned right now, being able to apply them effectively or even just getting them to work is something that will take weeks, months, or even like a year or so for you to really grasp, right? So the machine learning course that we're doing right now, the practical machine learning course, the objective is to expose you to what machine learning is, what real world machine learning problems look like, and what the process of training a machine learning model and using a machine learning model looks like, right? And once you get this high level picture, then over time, you can slowly chip away at small pieces, and this you will do via the assignments that we will have and via the project that you will do. But even over time, you can chip away at all of these small pieces and perfect each of these, right? This is not a skill that will come immediately, unlike, let's say, data analysis with pandas or just visualization with Plotly. I would say even those take time, but at least there are a fixed number of things you can do there. With machine learning, you have to apply a lot of thought, you have to apply a lot of creativity, you have to apply a lot of insight. There's a lot of experience that comes in. So don't be discouraged if you're not able to train good models initially. In fact, most machine learning models that you train initially will be pretty bad, but see that as an opportunity for improvement. Now, one good way to improve yourself is by going to Kaggle datasets and then clicking on the code tab. So here, for example, this is the rain in Australia dataset, clicking on the code tab and then filtering by most ports. And then you can check out some of these notebooks. People are very nice. They have created these public notebooks for you to check out. You can see that there is an extensive analysis and there is an extensive feature engineering and splitting and scaling and training and predictions and accuracy and scores and confusion matrices and classification metrics and a bunch of different things. This is honestly, it is a lifelong pursuit of machine learning, but I would also say that it is worth it because the kind of things that you can do with machine learning models is just amazing. It's out of this world, especially once you start getting into deep learning as well. So don't feel overwhelmed. Pick some data sets and try to create a model that works. And if you're unable to create a model that works, maybe read through what people have done with that data set, pick up some ideas from here and there, maybe copy paste some code if you need to, maybe even just run through this person's notebook, look at each line of code. And that is how you learn. The theory behind machine learning, you can probably watch a couple of videos and get a decent idea, but that is not going to help you beyond a point. What is going to help you is to try these things out on your own, on real data sets, on just like jumping into the pool without knowing how to swim, essentially, and just learning along the way, right? So that's what you want to do. And there are a lot of great resources, but you have to dig them. So you have to find great data sets, and then you have to read through these notebooks. As I suggested, one quick hack is go to a dataset, click the code tab and select sort by hotness. You can even add some filters if you want, but like language, Python and things like that, but sort by most words and just browse through the top 3 or 4 notebooks. And just like this, you will learn a lot about the different machine learning techniques. Now, one other thing I want to add here is that everything that we've done can be covered in each step can be covered in no more than 3 or 4 lines of code. So it may seem intimidating, the concepts may seem intimidating at first, but go through this notebook again, review this video, and once you get the concept, realize that the work to be done there is actually quite small. There may be some experimentation required, but the amount of coding is quite small. So here's what it looks like. The data pre-processing step. Downloading the dataset is 3 lines of code. You download using open datasets, you read it using rawdf, and then you drop NAs. So I've just dropped the rows which have rain today or rain tomorrow set to false or set to nan. Then creating training and validation datasets is 2-3 lines of code. Now we have used this because we have a date column, we have used like years less than 2015, equal to 2015 and greater than 2015. But we could also have used train test split, and that would also be just 1 or 2 lines. Then we created some inputs and targets by creating the input columns, the target columns, and then creating training inputs, training targets, validation inputs, validation targets, test inputs, test targets, etc. Then we have created some numeric and categorical columns just because we are going to need that information for the next steps. Then we imputed the numeric values by creating an imputer, fitting it to the data, and then transforming the training, validation, and test inputs. Imputing is simply filling in missing values. Then we have scaled the numeric features. So creating a scalar is again just 1 line of code. You create the scalar and then you fit it to the data. So it's going to figure out the ranges. There are other scalars too. There's something called a standard scalar you can check out. And then you apply them to the training, validation, and test sets. Again, scikit-learn has a very nice API where everything that you do in pre-processing, you first instantiate or create an object with some options, then you fit it to the data, and then you transform the data using it. One-hot encoding works the same way. You create a one-hot encoder, then you transform the data. And of course, when you transform the data, for each category, you're going to get a new column. So you also need to create a list of the new columns, and that's what this encoded columns is for. And then you apply that for the training, validation, and test set. Then you save the pre-processed data to disk. This is an optional step, but this is useful when you are working with large data sets so that you don't have to keep rerunning the notebook over and over and over. Some people also like to have a pre-processing notebook, a model training notebook, and a prediction notebook. And they would often put all those 3 notebooks in the same folder, and they would share these files across the 3 notebooks. So each time you improve something in pre-processing, you save it to the Parquet file, you read it in the prediction note in the training notebook, and then you save the model weights to disk, and then you read the model weights in the prediction notebook. Okay. And this is how you load the data. Now, what you should try and do is just try and explain each line of code above. And really there's about 15 lines for you to explain because most of this is just repeated code. So if you can explain these 10 to 15 lines, right? So you're just 10 lines away from understanding how to build machine learning models. Think of it that way and try to just work through understanding these 10 or 15 lines, and you will understand the pre-processing. Then you have model training and evaluation. So here we import logistic regression. Now, very interesting with the interesting thing with scikit-learn is that a lot of different models will have the exact same API. So instead of logistic regression, you could say a random forest classifier, you could say an SVM classifier, you could say a naive-based classifier, and they would work exactly the same way. You would have to change almost nothing except maybe just this one line. So here we are creating the model, we are instantiating the model using logistic regression, the constructor. Then we fit the model. Always is the next step. Fitting is where we go through this process of generating predictions, computing loss, improving the weights and biases, then again generating predictions, and keep repeating that process. Once we have fit the model, it's always a good idea to just check the accuracy or the score or whatever loss or whatever we are interested in. However, we want to evaluate the model on the training data, on the validation data, on the test data. And whenever you're happy with the results, you should save the model. And ideally, when you're saving them, you may also want to maybe just add like a small note here on what date you're saving it on, or just some kind of information in the file name so that you have multiple values. Now, the difficulty is then you run into these issues of like final one, final v1, v2, etc., etc. So what we recommend is that when you run jovian.commit, if you just attach the saved model with your Jovian notebook, so with every version, you can have a different version of your saved model that you can refer to. Okay. Again, try to explain each line of code in your own words. And if you can understand this, you understand how to train a model. You can even just try this out very quickly. Just change this to like a random forest classifier and just replace this with random forest classifier and see if you get a better result. The logistic regression is the simplest possible model for classification. Essentially, we are going to talk about decision trees and random forests next week, which are again a very interesting approach to the same kind of problem, and you'll see how they're able to get a better result. Then finally, your model is going to be used for prediction. So you need to have a way to very easily test your model, and always try and create this predict input function, which can take an input in the raw format or in a very human friendly format and return the prediction and the probabilities. In case of classification, or in case of regression, it's just a prediction, right? This allows you to experiment with the model, interact with the model one-on-one, because if you're saying this is an AI, a piece of artificial intelligence, then you should be able to interact with it in the same way you interact with a human, which is by giving it some input and getting some output out of it, and then interpreting it and comparing it with what a human would give you, right? And the closer it gets to the state of the art, or the closer it gets to the truth, the better, the more intelligent this model has become. Okay, so playing with and experimenting with individual inputs will give you a lot of insight into why the model is working or not working. Now you can see here that fitting the model is a very straightforward step, right? So there's not much you can change here. Maybe there are some parameters you can change here. And even calculating the predictions and accuracies is again a fairly straightforward step. You just run a couple of functions. But what will really give you insight in how to improve your model is by looking at the misclassified examples, which means the examples it was not able to predict correctly, or looking at the examples which it was unsure about, and then finally just playing with individual inputs. The kind of insight that this gives you is far more than any single accuracy score or any single number can give you, right? So definitely play with your model. And it's also very interesting to see, because once you've done all this work and trained this model, to see how it behaves, to see how it performs, to see what it thinks, essentially, right? The model's brain is those weights. That is a very important piece of understanding what the model is doing. I can go on for a long time about machine learning. This is my favorite topic, and I'm probably going to spend a long time just working on machine learning. That's why I feel very excited about it. But do try and I hope I was able to convey that same excitement to you, or the same power of machine learning to you, if not the exact details. But be patient with it. Don't expect all of it to come immediately, but when it does, you will be able to do some amazing things. And people will not believe the kind of things that you'll be able to do. So stick with it. That is what I'll say with machine learning. Okay. So here's a quick summary of what we've done: downloading the dataset, exploring dataset, splitting it into training, validation, and test, imputing missing values, scaling numeric features, encoding categorical columns, training a logistic regression model, evaluating a model using a validation set in a test set, and saving a model to disk and loading it back. There are even more steps that are involved in machine learning, which we will talk about in future lessons, and we will look at other types of machine learning models as well. And here are some more resources. If you want to look at the theoretical aspects of linear regression, logistic regression, you can watch these. You can watch these lessons. I think they're part of the machine learning course by Andrew Ng. That's a great course which gives you good theoretical foundation for machine learning, probably a good complement with this course. So it's on Coursera, Machine Learning, Stanford, Andrew Ng. You probably know the course already. Then here are some tutorials that I found useful while working on this notebook, especially this one, the extensive analysis, EDA modeling. I have borrowed a lot of things from this notebook, so do check it out. Every time I read a Kaggle notebook, I learn something, even after doing machine learning for several years. And if you want to try your hand at training your own logistic regression model, just spin up a new notebook and repeat each of these steps with one of these datasets. Breast cancer detection, this one should be relatively easy. Loan repayment prediction, this is very hard. And handwritten digit recognition, this is going to be intermediate, but you will have to figure out how to work with image data. Fortunately, all of these are hosted on Kaggle, and you can go and check the code tab, and on the code tab, you can always look at the most votes. So you can try something, and then you can, let's see, you can even search here. I'm just looking for logistic regression. Yeah, so you can see that there is this applied machine learning notebook, and this contains a logistic regression example somewhere. Supervised machine learning, there's probably a logistic regression example somewhere there. Logistic regression, There you go. So this is the logistic regression on another data set. That brings us to the end of today's lesson, logistic regression for classification. So what do you do next? Review the lecture video and execute the Jupyter Notebook. Complete the lecture exercises and start working on the assignment. Discuss on the forum, ask questions, share references, and help others. I will see you in the forums, and you can also find us on Twitter at @JovianML and @AkashNS. This was Machine Learning with Python 0 to GBMs. The next time we will look at decision trees and random forests. So do join us the next time as well. Thank you and have a good day or good night.